Hello students, welcome back. In this particular video lecture, I am going to start with you people the previous year questions discussion for GATE examination for the design of steel structures. So my dear students, let's start with our first unit, that is general design requirements. So our first question is, a steel section is subjected to a combination of shear and bending action. The applied shear force is V and shear capacity of the section is Vs. For such a section, high shear force, my dear students, I had discussed with you people, when value of V becomes more than 0.6 Vs, value of V becomes more than 0.6 Vs. In this particular situation, or more than or equal to, you can say, then our section is defined as a high shear case. Otherwise, a section is designed as a normal shear case or a low shear case. So my dear students, this was our question number first, for which option number A is correct. Our question number 2, the cross section of a thermomechanically treated reinforcing bar. Basically, it's a question of you can say RCC design, in which the inside portion is a soft perlite core, and outside the basically you can say a hard materialistic rim is there, which is having outer core as well as the inner core, So this is called as basically the hard materialistic rim, and this soft perlite core is there. So our option number basically C is correct option for this particular question. Our question number 3 is, the permissible stress in axial tension, that is sigma AT. Basically, as we know that for sigma AT is basically 0.6 Fy, whereas sigma BT is equal to 0. That is bending tension. Sigma BT is equal to 0.66 Fy. Please be careful. We had discussed during our theoretical discussion 0.66 Fy. Okay. So our next question is, factor of safety adopted by IS 800/1984 while arriving the permissible stresses in axial compression. As we know that, my dear students, sigma AC is equal to 0.6 Fy, and as we know that our factor of safety is defined as the yield stress Fy whole divided by the permissible stress, that is 0.6 Fy in this particular case. So after solving, I found the value as 1.67. Please be careful. This factor of safety of 1.7 is applicable for short columns, beams and tension members in general. So this is applicable for beams, tension members and short columns, tension members and short columns in basically in compression and tension, axial compression and tension. Whereas for long columns, this value is not equal to 1.67. This factor of safety is taken as 1.92. Very important value is there. This is our answer. So our option number C is correct, that is 1.67. Okay. Now let's discuss with question number 5. The permissible bending tensile stress in high strength deformed bar. My dear students, actually this is not the question of a design of steel structure. This is the RCC questions for FE 415, that is FE 415 grade, that is HYSD bars, high yield strength deformed bars, or you can say cold twisted deformed bars or CTD bars. As we know that sigma is ST sigma st is equal to 230 megapascal. Sigma st is equal to 230 megapascal. Please be careful. However, for Fe250 this value is 130 megapascal in you can say for compression zone, and 140 megapascal for the tension zone, whereas Fe415 sigma SC value is 190 megapascal, but here in tension the value is 230 megapascal. So our sixth question is factor of safety adopted by IS 800 1984 while arriving the permissible stress in axial compression. This is also the same question as we had discussed. Sigma SC and you can say sigma AC, that is 0.6 Fy, and as we know that factor of safety is equal to Fy divided by the permissible value, that is 0.6 Fy. After solution I found the value equals to 1.67. so our option number C is correct. Okay, now question number 7. Generally the maximum deflection to the span ratio, L by D ratio, for a steel member should not exceeds, and as we know that, my dear students, as per working stress method, delta maximum shall not be more than L divided by 325 or 300, but here option is not given, so our option number C is correct, 1 by 325. Question number 8. Which one of the following is not correct? Please be careful. Here false statement is asked. Not correct for steel section. The maximum bending tensile stress in tension and in compression, extreme fiber calculated on the effective section of a beam shall not be bilkul. This is okay. 0.66 Fy. This is okay. The bearing stress, obviously this value is also okay because the bearing stress shall not exceed 0.75 Fy. The direct stress in compression on cross section, obviously this is sigma AC. He is talking about sigma AC here. He is talking about sigma BC or sigma BT here, and here sigma P value is discussed. All these three statements are correct. So these are basically, you can say, correct statement here. These are correct statement, but in exam, in question, it is not asked. It is asked not correct. So our none option number D, that is none of the above, is correct. So my dear students, these were the questions of our unit number 1. So now let's start with the question of unit number 2, that is connections. Very important questions are there. Please be careful. Unit number 2. Okay, let's start the questions of unit number 2. That is the design of connections. So our first question is, in a fillet weld, the direct shear stress and bending tensile stresses are 50 megapascal and 150 megapascal respectively. As per IS 800 2007, the equivalent stress, as we know that, my dear students, the resultant stress in this particular situation, Fr, is equal to whole under root of, we had discussed during the discussion of our beam sections. So this is our sigma square plus 3 times of tau square. Yes or no? We had discussed or not? We had discussed. So here this is 150 megapascal is given plus 3 times of, sorry, this is 50 megapascal, and this is okay, 150 megapascal, and the bending tensile stress is given as 150, and this is 50. 3 times of 50 square whole under root. After solution I found the value as 173.20 megapascal. This is GATE 2019 question. So our answer is 173.20 megapascal. 20 megapascal. This is our okay. Here sigma is given as 150 megapascal and tau is given as 50 megapascal. So please be careful. This is our answer, 173.20 megapascal. Now, second question is, a fillet weld is simultaneously subjected to a factor of normal and shear stress of, same question is there. So equivalent stress, we have to calculate the equivalent stress. We have to calculate equivalent stress. And as we know that equivalent stress is equal to whole under root of sigma square plus 3 times of tau square. So here all the values are given. Here normal stress is given as 120 megapascal and the shear stress is given as 50 megapascal, 3 times of 50 whole square whole under root. After solution, I found the value equals to 147.99 megapascal. So you can round off the value to 148 megapascal. You can round off the value to 148 megapascal. So now let's move towards our question number 3. A steel member M has a reversal of stress. Obviously, if reversal of stress means alternate tension and compression. Alternate tension and compression due to live load, due to influence line diagram. Whereas another member N has reversal of stress due to wind load. Please be careful. As per IS code number 800/2007, the maximum slenderness ratio permitted. My dear students, due to effect of the, you can say, due to effect of the live load, if reversal of stress occurs, then our maximum slenderness ratio equals to basically 350 megapascal in a roof truss is basically, lambda is equal to 350. Lambda is equal to 350, and due to wind load, the value is 180 megapascal or 180. Lambda is equal to 180. That is basically non-dimensionless parameter. So less for member M and then that of the less for member N, because less for member M and less for member more for member N. That is the value of the slenderness ratio. So this is basically the comparison. So here reversal of stress due to live load, my mistake, it is 180. It is 180 and it is 350. It is 350. So here the values are and this value is 180 and this value is 350. Value of lambda. Okay, now let's move towards our question number 4. Prime forces are basically, my dear students, the tensile forces due to flexibility in between the connected portions. Likewise, if these two portions has to be connected, then if due to the tensile force, if there is some flexibility occurs here, likewise this, so the forces responsible are called as the prime forces. Forces responsible are called as the prime forces. So you can say the tensile forces due to flexibility of the connected portions, connected parts. These are the connected parts. So our question number 5 is, in a steel plate with bolted connection, the rupture of net section. Rupture means basically a tensile failure, because ruptures are generally failures under the tension rupture, shear failure, etc. Likewise that. So basically this happens in the tension members. Rupture modulus of rupture, and as you can also calculate the rupture strength, that is equal to FCR is equal to 0.7 times of whole under root of FCK. FCK is nothing, that is the characteristic strength of the member or characteristic strength of the concrete to be used. We have to check that particular section for the tension. Okay. So now let's discuss with our question number 6. For a fillet weld of size S, as shown for the adjoining figure, the effective throat thickness, my dear students, as we know that effective throat thickness is equal to K into S, and K value is equal to 0.7 when the angle lies in between 60 degree to 90 degree. This value is equal to 0.65 when the value lies in between 90 degree to 100 degree. So here 0.65S is the correct option. 0.65S is the correct option. So our question number 7th is rivet value is defined as, and as we know that our rivet value RV is equal to minimum of PS and PB of a single rivet. PS and PB of a single rivet. PS and PB of a single rivet. Okay, so our option number A is correct. Lesser of the bearing strength of rivet and shearing strength of a rivet. Question number 8. Identify the most efficient butt joint. And as we know that, my dear students, the most efficient joint is that joint which gives the maximum value of PT. PT value should be maximum, and PT value will be maximum when less number of deductions are there at critical sections. Likewise, at this particular section and at this particular section, these are the critical sections. So we can say that PT value is minimum in diamond type of riveting. In diamond riveting, PT value is maximum. So our option number A is correct. That is the most efficient butt joint with double cover plates. Question number 9 is generally fatigue life of a welded structure or fatigue life of a riveted steel structure ratio is basically you can say fatigue life of a welded steel structure is generally more than fatigue life of a riveted steel structure, that, and hence we can say that the ratio of a fatigue life of a welded structure to the fatigue life of a riveted steel structure is always less than 1, because welded connections are prone to cracking, because welded connections are subjected to cracking. Welded connections are subjected to cracking, prone to cracking. Welded structures are subjected to cracking. Therefore, fatigue life of a welded structure, fatigue means cyclic and recyclic loading continuous. Fatigue means cyclic and recyclic loading continuous. Fatigue life of welded structure is always less than fatigue life of riveted structure. Fatigue life of a riveted structure, because riveted structures are basically, you can say, the temporary connections or permanent connections, and also the welded structures are also the permanent connections. However, the bonded connections are the temporary connections. Riveted structures. Okay, so my dear students, let's move towards our question number 10. As per IS code number 800 1984, the minimum pitch, and as we know that, my dear students, the minimum pitch is 2.5 times of the nominal diameter of the rivets. 2.5 times of nominal diameter of the rivets. However, the maximum pitch may be 12 times of the, or 12 times of T minimum, or 200 mm or 300 mm. Various cases were there. We had discussed about the specifications of the pitch, rivet value, gauge distance, etc. during our theoretical discussion. Okay, so our 11th question is, effective section of a fillet weld is represented by a triangle ABC with sides S1, S2 and S3 and S4. such that S3 is more than S2 and it is more than S1. If allowable shear stress in the weld material is tau, resistance of weld material per unit length is, and obviously my dear students, the welded structure always fails through this particular section, and this particular section is called as the throat plane. This particular section is called as the throat plane. So always the shear stress, because weld is a weak in shear, so here shear failure happens. Here shear failure happens throughout. Shear failure happens throughout the you can say the throat plane, PLANE, shear failure. Okay, so the effective throat thickness calculated according to length S4, not S1 and S3. So S4 into tau is the correct option. S4 into tau is the correct option. That is resistance of weld per unit length. That is resistance of weld per unit length. Resistance of weld per unit length is equal to S4 into tau. S4 into tau. So our option number D is correct. That is S4 into tau. Okay. So my dear students, our 12th question is, a group of rivets at a joint is subjected to in-plane torsional moment of M. The rivet value have finished areas of A1, means all areas are the same, and distance Ri, R1, R2, R3, R4, R4 and maybe there from the CG of the rivet group. The shear force developed in ith rivet means any kind of the rivet, is equal to, and as we know that my dear students, here the moment is also developed, so moment is also developed, so that is equal to basically the torsional shear force in ith rivet, Fu, that is torsional shear force in ith rivet, and as we know that this is equal to M into Ri into Ai divided by Ri whole square, or J, you can say polar moment of inertia. This is calculated by the formula tau by R is equal to G beta by L is equal to T by IP, and here torsional shear force or torsional moment is converted as the moment M M. So this is equal to, and whereas J is the polar moment of inertia, so we can say that it is proportional, not the directly proportional, it is inversely proportional to polar moment of inertia of the group of areas, because polar moment of inertia IP is equal to, it is nothing, algebraic sum of AI Ri whole square, that is equal to the polar moment of inertia, or J. J is sometimes also called as the IP value. Sometimes it is called as the IP value, that is the polar moment of inertia. Now our question number 13, that is a very important question is there. That is basically the design question is there. A 16 mm thick gusset plate is connected to 12 mm thick flange. Actually, my dear students, this type of question we had discussed in our, you can say, theoretical discussion. So here initially we have to calculate the value of the direct shear stress. Our step number 1 is, initially we have to calculate the value of direct shear stress. Q is equal to, as we know that, P divided by 2HT. Here P is given as 350 kilonewton. 2 into H is given as 500 mm total depth. This is our value of H is there, and T, that is thickness, connected thickness is given as 16 mm. So P is 350, P is 350 into 10 to the power 3 whole divided by 2, H is 500, T is 16. After calculation, value is 21.88 megapascal. Now one value is okay. Now we have to calculate the bending stress also. We have to calculate the bending stress according to the Flexner formula. Flexner formula, F is equal to M divided by section modulus, M divided by Z. Z is equal to I by Y maximum. So here moment is basically force into eccentricity, So force is 350 kilonewton, and 350 into 10 to the power 3 into eccentricity is 100 mm. That is the eccentricity. This value is the E value, eccentricity value, whole divided by Z, section modulus, and Z is I divided by Y maximum. I is polar moment of inertia, and you can say Z is equal to basically BD square by 6, BD square divided by 6. So this is 16 into 500 square, BD square divided by 6, and 6 half is 3, so it is above. So after calculation, I found this value equals to 26.25 megapascal. This value is equal to 26.25 megapascal. So here we have Q value, we have F value. Now we can easily calculate the value of the resultant stress. So my dear students, here our resultant stress is equal to, whole under root of the F square plus 3 times of Q square, that is equal to F value we have calculated, that is 21.88, and sorry, Q value, and F value is equal to 26.25, 26.25 square plus 3 times of 26.88 square. So after making the whole under root of this thing, our final answer is equal to 46.09 megapascal is our answer. So my dear students, in this particular question, basically this is you can say the in plane eccentric welded connections are there. Here we have calculated the Q value, F value using the given data, and finally our answer is 46.09 megapascal. 46.09 megapascal is our answer. Okay, so my dear student, let's move towards our question number 14. So our first 14th number question is 4 volts PQRS of equal diameter are used for a bracket. Bracket means a small piece of a maybe angle, maybe channel. Here small piece of a plate is used. Here this bracket is a small piece of a plate. This is small piece of plate. Small piece of plate. Here it is used. Subjected to a load of 130 kilonewton as shown in the figure. So my dear students, this type of connections are called as the in plane eccentric riveted connections. Yes or no? Yes, we had discussed. So we have to calculate the resultant force in the rivet P, means we have to calculate the force in this particular rivet, this particular bolt. Here the direct shear force occurs likewise this, and this is F2 value and this is F1 value. The angle is theta, and from the CG of the rivet group, radial distances are same for all the kinds or all the 4 rivets P, Q, R and S. So my dear students, let's calculate the value of F1 first. F1 is the force in each bolt or direct shear force in each bolt. So our first step is, if I am talking about the solution of the problem, our F1, that is direct shear force in each bolt, will be equal to this 130 kilonewton force has been divided into equal parts to the all four rivets, and this value is our 32.5 kilonewton. 32.5 kilonewton. Similarly, F2 value, that is the force due to twisting moment. Twisting moment is 130 into this eccentricity, that is 200 mm. So P into E into Ri, P into E into Rp, rivet in the force P, radial distance for the rivet, for the rivet P divided by Ri whole square, summation of Ri square. So here P is 130 kilonewton. This is our, after putting in the values, P is this one. This is our eccentricity E. Radial distance. Radial distance for all the rivets is same, that is this plus this whole square. So this value is 50, this value is 120. So rivet value, radial distance value for P, radial distance for rivet Q, radial distance for Q rivet R, and radial distance for rivet S is equal to same, that is equal to whole under root of 120 square plus 50 square, that is same. So after putting all the values, we can easily calculate the value, and this value is equal to 50 kilonewton. Now we have F1, we have F2. Now resultant can be find out using the value of theta. Theta value is simple, that is the tangent of theta is equal to perpendicular divided by base. So tangent of theta is equal to perpendicular is 120, base is 50. So after calculation, I found the value of theta is equal to tangent inverse of 120 by 50, that is 67.38 degree. So we have all the values of F1, F2 and theta. Now resultant can easily be find out using the vector rule, using the parallelogram rule. So resultant force in rivet bolt P. So resultant force on bolt P is equal to whole under root of F1 square plus F2 square plus 2F1 F2 cos theta. Yes or no? Now F1 was our 32.5 kilonewton, F2 is equal to 50 kilonewton, 2 F1 32.5, F2 50 into cos theta is 67.38 degree. So we have to put into the under root. So this value is equal to 69.32 kilonewton is our answer. Okay. So my dear students, resultant force on bolt P is equal to, calculated using vector rule, 69.32 kilonewton is our answer. So here our option number B is correct option. Option number B is correct option. Okay. So my dear students, this was our question number 14, in which we have to calculate the value of the force in the bolt P, in the rivet P, that is the most critically stressed rivet. Okay. Now let's move towards the next question, that is question number 15. Okay. Two plates of 8 mm thickness each are connected by a fillet weld of 6 mm thickness, means here size of a fillet weld is given as 6 mm. The permissible stress in the plate and the weld material are, means Fs is given as 150 megapascal and 110 megapascal respectively. Assuming the length of the weld shown in the figure, so length of the weld is 100 plus 50 plus 100, that is basically 250 mm. So calculate the effective length of the permissible load to the effective length, and the permissible load we have to calculate. We have to calculate this value of the permissible load P. P value we have to calculate. Okay. So my dear students, let's initially calculate the maximum load taken by the plate. The maximum load taken by the plate initially we have to calculate. So if I am talking about the solution of this particular problem, okay, so the maximum load taken by the plate, maximum load taken by the plate, and that is equal to basically this is maximum load value taken by the plate is equal to 150 into 50 into thickness is 8. This is the maximum load. That is equal to, after comparing all the values and converting the value into kilonewton, this is 60 kilonewton. Now maximum load taken by the effective weld sorry, so that is equal to effective throat thickness into L effective into the permissible stress in the weld. Maximum load taken by weld is equal to effective throat thickness, that is K into S, into effective length of the weld into whatever the value of the stress applicable in the weld material. Okay, now here K value, since the angle in between these two plates is 90 degree, so K value is 0.7 into S, size of weld is given as 6 mm, into effective length of the weld is 100 plus 50 plus 100, that is 250, into Fs value is given as 110 megapascal in the weld material. After calculation I found this value equal to 115.5 kilonewton. So permissible load will be 60 kilonewton and 115.5 kilonewton less value. That will be the permissible load, because if we apply the load more than 60 kilonewton, then obviously plate will fail, and if we apply the only, let us suppose, 115.5 kilonewton load, then obviously weld will be safe but plate will be failed. That's why our true answer is 60 kilonewton. So hence permissible load is equal to 60 kilonewton. Here value is 60 kilonewton is our answer. Okay. So my dear students, in this particular type of problem we had discussed about the how to calculate the maximum load taken by the weld material and the permissible load. Permissible load is minimum of the two values. Permissible load is minimum of these two values. That is the minimum value. Okay. Now let's move towards our question number 16. A column is subjected to a load through a bracket as shown in the figure. Same question is there. So here P value is given as 10 kilonewton and eccentricity is given as 15 centimeter. This is our eccentricity. This is P value. Now radial distances will be same, because all the radial distances are given. This is radial distance, this is radial. So radial distance from here to here for any kind of the rivet is 5, 5, 5 and 5 for all the rivets, that is R1 and R2, R1, R2, R3, R4 are equal to 5 centimeter. Okay. Now same fundamentals are there. Initially we have to calculate the value of F1, F2 and then resultant. So our F1 value is equal to basically 10 divided by 4. Our F1 value is equal to 10 divided by 4. Our F1 value is equal to, okay, this value is equal to 10 divided by 4, that is 2.5 kilonewton. That is okay. This is also the in plane eccentric welded riveted connections. Now force in the bolt due to moment F2 is equal to P into E into radial distance divided by all radial distances square. 4 times of radial distance square is 5 square. So this value is equal to 7.5 kilonewton. Now let's calculate the value of theta. Theta calculation is very simple. From here to here, this value, if this is theta, this is adjacent value of F1 and F2, so this will also be theta. Okay, so tangent of theta is equal to basically 5 divided by 5, or you can say this theta is equal to, since we have to calculate the resultant force in the bolt number 1, so here the directions are likewise this. This is F2, this is equal to F2, and this is our F1. This is our F1. So here theta is basically 135 degree, because here theta is tangent theta is equal to 1. So here theta is equal to 135 degree. Please be careful. 35 degree, here 45 degree. Tangent theta is equal to 1. Tangent theta is equal to 1. So theta is equal to 45 or 135 degree. So we have all the values of theta and that extra every values we have. So we can easily find out the resultant force in rivet number 1. FR1 is equal to F1 square plus F2 square plus 2F1 F2 cos theta whole under root. So that is equal to whole under root of F1 is 2.5 square plus 7.5 square plus 2 F1 F2 cos 135 degree. After solution I found the value equal to 5.99 kilonewton. 5.99 kilonewton is our answer, or nearly equal to 6 kilonewton. So resultant force is equal to 6 kilonewton is our answer. Okay, please note it down very fast. This was our question number 16. So our next question, question number 17, is very simple question is there. Two bolted plates under the tension with alternative arrangement of bolt holes likewise this and likewise this are shown in the figure 1 and figure 2. The hole diameter, pitch, gauge length et cetera are respectively B, D, P, G et cetera. Which one of the following conditions must be satisfied to ensure to have high tensile capacity? High tensile capacity, that is a very important fundamental. High tensile capacity for configuration as shown in the figure. My dear students, as we know that for the maximum efficiency condition is B minus the number of the holes in figure 1 and figure 2. In figure 1 only one rivet hole is there. In figure 2 two rivet hole has been deducted from the total width of the plates. Total width of the plate are given here. Likewise here this is also given as B value. Okay, this is given as B value. Okay, in the same case for the figure number 2 B is also the same. So for the figure number 2 B minus 2D plus P square, whatever the pitch value, P square divided by 2 times of gauge distance into thickness must be more than or equal to the figure number 1 value. Figure number 1 value is B minus D. Only one rivet hole has been deducted. only one rivet hole has been deducted. Here also thickness will be multiplied, so B minus D into T, So from here you can easily calculate the condition for which examiner asked P square divided by 4G should be more than or equal to D. So this implies the condition P square should be more than 4 times of G, because for analysis purposes we have calculated the value. So our answer is 4G into D, my mistake, 4G into D. So our option number C is correct option. P square should be more than or equal to 4G into D. Okay, now let's move towards the question number 18. Two plates are connected by a fillet weld of the size 10 mm and subjected to a tension as shown in the figure. The thickness of plates is 12 mm, means plate thickness are 12, size of weld is 10 mm. Yield stress and ultimate Fy value is 250 megapascal, Fu value is 410 megapascal. Welding is done in the workshop. Workshop means 1.25 partial factor of safety is taken. If it was done in the field, then partial factor of safety has been taken as or will be taken as 1.50. As per the limit states method of the IS code number, limit states method code, that is 800/2007 amended, the minimum length of each weld to transmit a force equals to 270 kilonewton is equal to, so we have to calculate the length of the weld initially basically. So since the total force is 270 kilonewton, so force carried by single plate will be equal to force carried by single plate, force carried by single plate, force carried by single plate is equal to 135 kilonewton, that is equal to 270 divided by 2. So this total force must be equal to the force formula from where we can easily calculate. So 135 into 10 to the power 3, that is equal to force calculated since limit states method is used, Fu divided by von Mises Henkai theory, distortion energy theory, 1.25 into L effective we have to calculate into effective throat thickness, that is ETT. So this ETT is simple, that is 0.7 times of 0.7 times of S, that is S is given as 10 mm. S is given as 10 mm. Size of the weld is given as 10 mm. Okay. So from here, after calculation, this value we can calculate the value equals to the LFA or Fu is given as here as, and that is 410 megapascal. Fu is 410 megapascal. So after calculation, we find the value of L effective. L effective is equal to 110 mm. 110 mm is our answer, because examiner asked us to calculate the value of L effective length in the multiples of 5, not in the multiples of or not the round of value. So our answer is 110 megapascal. That is our simple calculation. Okay, so now let's move towards our question number 19. A bracket plate connected to a column flange. The same question is there as we had discussed in the in-plane eccentric welded connections. Connected to a column flange, transmit a load of 100 kilonewton as shown in the figure. So my dear students, initially we have to calculate the direct shear force, that is F1 value. Initially we have to calculate the value of F1, that is 100 divided by 4. Then we have to calculate the F2 value, P into E into Ri in divided by whole Ri square. So here P is 100, eccentricity is 600, Ri radial distance we have to calculate, that is this square Pythagoras theorem plus this square whole under root. we have to calculate the radial distance r value. So Ri value is the simple 75 under root of 2, 75 under root of 2 multiplied by 10 to the power minus 3 to convert the value into kilonewton, and then 4 radial distance is 75 whole under root of 2 10 to the power minus 6. After calculation I found the value equal to 141.42 kilonewton. Since all the distances are same, here all the distances are same, so tangent theta is equal to 1, so tangent theta is equal to 1, so you can say theta is equal to 45 degree for the most critically stressed rivet. For the most critical, and most critically stressed rivet is rivet number 1. This is our most critically stressed bolt. This is our most critically stressed bolt. So F resultant will be equal to the same whole under root of that is 25 square plus 141.42 kilonewton square plus 2 F1 F2 cos 45 degree. So this value, after calculation I found the value of resultant force is equal to 156.2 kilonewton is our answer. Okay, that is a very simple calculations are there for the correction, most critically stressed rivet. Okay, now let's move towards the next question. Question number 20. The tension and the shear force, basically this is the type of, you can say, the interaction chart questions. This is the type of the question. Okay, so here we have to calculate the value of tangent of theta, cos theta, sin theta initially we have to calculate, because this force has to be resolved. If I resolve the components, one component will be in the horizontal direction, this is the net resultant force, and one component will be in the vertical direction. If this is pu, so if this is theta, then this will be pu cos theta, and this will be pu sin theta. So here distances are given. So here tangent of theta is equal to perpendicular divided by base, that is 3 by 4. Cos theta is equal to 4 by 5, that is base upon hypotenuse, and sin theta is equal to 3 by 5, that is perpendicular upon hypotenuse. Okay, now tension force in each bolt initially we have to calculate. Tensile force in each bolt, tensile force in each bolt is equal to 4 pu, means tensile force 4 pu divided by 5 into 6. From here this value comes, because my dear students, pu cos theta is equal to nothing, that is 4 pu divided by 5. 4 pu divided by 5, and this total force has to be resisted by all 6 number of the rivets. 6 number of rivets. This force has to be resisted by all 6 number of the rivets. This is the same thing. Okay, so here we can say n value is equal to 6. Okay, similarly a pu sin theta will be equal to 3 pu divided by 5. This is also equal to 3 pu divided by 5. That is okay. Now shear force in each bolt will be equal to, then we have to calculate. pu is given as a 250 kilonewton. So this value is equal to 4 into 250 whole divided by 30. After calculation I found the value equal to 33.33 kilonewton. Okay, now shear in each bolt. Initially we have to calculate the shear force in each bolt. Shear in each bolt, that is equal to 3 pu divided by 5 into 6. 3 pu divided by 5 into 6, so 3 into 250 divided by 5 into 6, that is equal to 25 kilonewton. That is equal to 25 kilonewton. So my dear student, these two values we have to calculate, or we had to calculate, and our final answer is 33.33 and 25. So our D option is correct. So our D option is correct option is our answer. Okay, this was our 20th question, question number 20. Okay, now let's move towards question number next. Let's move towards question number next, that is 21st question. Two plates are connected by the fillet weld. Two plates are connected by the fillet weld of size 10 mm and subjected to tension as shown in the figure. Thickness of each plate is 12 mm. Yield stress and ultimate stress are given. Welding is done on the workshop as per limit states method. Minimum length nearest higher multiple of each weld. This type of problem we have calculated. This type of problem is repeated, and we have calculated the value equals to 110 mm. 110 mm. This value we have to calculate, or we had calculated in the above problem. This problem was same as that we had discussed in our you can say problem number. Let me check the problem number of that particular thing. We have calculated problem number 18. We had discussed the same thing, 110 mm. Okay, so our next question, question number 22 is: a double cover butt joint DCBJ is used to connect two flat plate of 200 mm thickness. This and this thickness, 14 mm thickness. There are 12 power driven rivets PDFR of 20 mm diameter at a pitch of 50 mm in both the directions as shown in the figure. Two cover plates of 10 mm are used. In above situation and the below double cover butt joint are used. Capacity of the joint in tension considering bearing and shear only, with permissible bear and shear stresses are this one. So we have to calculate the capacity of the joint in the tension as well as in the tension as well as in compression, or shearing and bearing both effect. So my dear students, here the gross diameter initially we have to calculate. Gross diameter will be equal to 20 plus 1.5 mm. Gross diameter of the rivet D, that is equal to the gross diameter dia is equal to 20 plus 1.5 mm, that is 21.5 mm. Okay, now since double cover butt joint is used, so rivets are subjected to double shear and bearing only. Since double cover butt joints are used, so rivets are subjected to double shear and bearing. Double shear and bearing. So shear strength of the rivet in bearing means is PS. If we calculate total number of rivets are, or for a single rivet, that is we have to calculate. So pi by 4 d square 2 for double shear, pi by 4 d square, that is 21.5 square, into PS value is given as, FS value is given as the 100 megapascal, 100 into 10 to the power minus 3, that is equal to 72.61 kilonewton. Similarly, PB, in the value of the PB, projected area is there, D into T minimum. Now T minimum is 14 mm and 14 mm. So you can say, or you can say here T minimum is taken as T minimum is equal to either 14 mm or 10 plus 10, that is 20, sum of cover plate thicknesses. So our value will be 14 mm. So T minimum is equal to 14 mm. T minimum is equal to 14.0 into FB value is given as 300 megapascal. 300 into 10 to the power minus 3. After calculation, I found the value equal to 90.3 kilonewton. 90.3 kilonewton. So our rivet value is the minimum of these two. Rivet value RV is equal to 72.61 kilonewton. That is the minimum value. That is the minimum value. Okay, 72.61 kilonewton. Now capacity of the joint is equal to rivet value into the, you can say, the number of rivets. Number of rivets are 12. So we can easily calculate the capacity of a joint. How much load a joint can take. That is called the capacity of the joint. Capacity of the joint that we have to calculate, that is equal to 12 number of rivets, and one rivet can easily handle the load of 72.61 kilonewton. So after calculation, I found the value equals to 871.32 kilonewton is our answer. This is our answer. Okay, capacity of the joint. So this we have to calculate. So our 871.32 kilonewton, that is B option, is correct option. B option is correct option for the question number 22. Now let's move towards our question number 23. Two plates subjected to direct tension, each of 10 mm thickness, having width of 100 mm and 175 mm respectively, are to be fillet welded with an overlap of 200 mm. So give the permissible weld stress 110 megapascal, permissible stress in steel 150 megapascal. So the maximum force in smaller plate that can resist is equal to, we can calculate length of the weld required, we have to calculate, and that is calculated using the maximum force. So P maximum we have to calculate in the plate. P maximum for the plate element initially we have to calculate, that is 100 into 10 because 10 is thickness, into 150 is the permissible stress, that is Newton, that is equal to 150 into 10 to the power 3 Newton, or you can say 150 kilonewton. Now thickness of plate is given as 10 mm. So square edge, for square edge S maximum is equal to T minus 1.5 mm, for, because here not rounded edge is there, here square edge is there. For square edge connection, S maximum is equal to T minus 1.5 mm. However, for rounded edge it was 3 by 4 times of T minimum. Okay, now this is equal to 10 minus 1.5, that is equal to 8.5 mm. 8.5 mm. Now we can calculate the strength of the weld. Strength of weld is equal to strength, that was basically strength of plate. Now we are going to calculate strength of weld, is equal to effective throat thickness 0.7 times of S into permissible weld stress is 110 megapascal, that is given to us. Okay, so this value is equal to, after calculation, S value is maximum value taken, maximum value is taken as 8.5. so after calculation I found the value equal to 654.5 Newton per mm length. Now length can easily be calculated by the strength, P maximum divided by the strength, then length is calculated. So here length of the weld required for resisting maximum force, length of the weld required for resisting, length of weld required to resist P maximum, that is equal to L is equal to P maximum whole divided by a strength of weld whole divided by strength of weld. Now P maximum was 150 whole divided or into 10 power 3 divided by, because Newton per mm is the our strength of weld, that is 654.5 Newton per mm. So our final units will be mm, and after calculation I found the value equals to 229.18 mm is our answer. So let's match the answer with the given options. Let's match the answer with the given options. So our 229.20 is the closest answer. So our B option is correct. Our B option is correct. Okay. Now let's move towards question number 24. So our question number 24 is, a 12 mm thick plate is connected. This question I had discussed with you people during our theoretical discussion, in which we have to find out the rivet value. Since rivets are subjected to double shear, so rivet value is equal to minimum of PS and PB. Minimum of PS and PB. Rivets are subjected to double shear. One shear plane, second shear plane. Okay. So double shear is there. So PS is 2 pi by 4 gross dia square. Here the diameter of rivet is not given. So initially we have to calculate the diameter of the rivet. Nominal diameter of rivet is not given, so we have to calculate. So phi n by Unwin's formula 6.04 under root of T minimum. T minimum is 8 mm. T minimum is 8 mm thickness, sorry 12 mm thickness. Minimum of 12 and 8 plus 8, that is 12 mm. Okay. So that is equal to approximately 16 mm. So our gross diameter will be equal to 17.5 mm. That's okay. 2 by 4 d square 17.5 square, and the permissible values are given as 90 and 270 megapascal. So 90 into 10 to the power minus 3, that is the PS value, shear strength of a single rivet. Now PB value, projected area, DT minimum 17.5, T minimum is 12 into and that is 270 into 10 to the power minus 3, that is PB value. After calculation I found the value equals to, the minimum value is equal to, this PS is equal to 43.29 kilonewton, 29 kilonewton, and PB value is equal to 56.7 kilonewton. So our minimum value is 43.29. So that is equal to our 43.29 kilonewton is our answer. Okay. Now let's move towards our question number 25. Rivets and bolts are subjected to this particular condition, tau VF both shear stress and the axial tensile stress, so proportionate that stresses do not exceed the respective allowable stresses tau VF and sigma TF. So the value of tau VF calculated divided by tau VF plus sigma TF calculated by sigma TF. Obviously my dear students, here no limit word or ultimate word is used. That's why this follows the working stress method, and this shall be less than or equal to 1.40. So our C option is correct, 1.40. Question number 26. A steel flat plate of rectangular section of size 70 by 6 is connected to a gusset plate by 3 bolts as shown in the figure, having shear capacity, means bolt is having the maximum shear capacity of 15 kilonewton and whole diameter is 11.5 mm. Allowable tensile stress is 150 megapascal. Maximum tension we have to calculate. That can be applied to the flat. Flat means ISF is there basically. This is our ISF, Indian Standard Flat. ISF, Indian Standard Flat is there. Okay. So my dear students, very simple problem is there. Initially we have to calculate the value of the shear force or maximum tension you have to calculate. Here thickness is given, thickness is given 6 mm, width is given 70 mm, nominal diameter is given 11.5 mm, and strength is given 150 megapascal, and or pitch and gauge are given as 35. Pitch is equal to 35. This is our pitch value. This is our pitch value, and gauge distance is basically you can say 20 mm. G is equal to 20 mm, and distance and edge distances are given as 15 mm. So maximum force applied on the flat, let us suppose T force is there. So this is our maximum force. This we have to calculate. This maximum force we have to calculate. Okay, so various cases may be there. Various cases we have to discuss. Case number 1. Case number 1, by assuming by failure of all the bolts in the shear. First case is by failure of all bolts in shear. All the bolts in shear. That is a very important fundamental. So that maximum tensile force will be equal to 3 bolts are there. Shear capacity of each bolt is 15 kilonewton. So the value is 45 kilonewton. Value is 45 kilonewton. So our answer is basically A option shall be there. A option shall be there, but A option shall be there. Now we can also calculate the value by different fundamentals. By another fundamentals also. Case number 2. Case number 2. By tearing of a flat at section 1:1. Tearing of a flat, because failure may be tearing, shearing and bearing of flat at 1:1 section is there. That is at this particular section. This is our section number 1:1. This is our section number 1:1. Only one rivet hole has to be detected. So here tensile force is equal to B minus D into T into sigma 80, that is 150 megapascal. That is given. Okay. T, that is given. Okay. Now B is equal to 70. 70 from where 70 comes? 20 plus 20 plus 15 plus 15, that is 70, minus gross diameter is equal to given as whole diameter, because whole diameter is called as the gross diameter, 11.5 mm. So 11.5 into T minimum is simple, that is 6, that is given, into 150. So this is equal to 52.65 kilonewton. Now case number 2. Two values we have, 45 and 55, 52.6. Now there may be chance the section may also fail along any kind of the section. Likewise this section may be failure. S square by 4g rule may be there. S square by 4g rule may also be applied. So case number 3. Case number 3. If failure happens likewise this. If failure happens likewise or along this section or this section, this is our section number 3.3. Section number 3.3. So failure may be may happens along any kind of the section. Please be careful. Section may fails along any kind of the failure. So my dear students, by tearing of the flat at section 3.3, where we have to apply S square by 4g rule, by tearing of given flat at section 3.3. At section 3.3, so we have to apply the s square divided by 4g rule. S square divided by 4g rule in all the 3 sections. Total 2 rivets may be there, but all 3 rivets has to be deducted from the total width. So let's calculate the value. So that is equal to P value is equal to B minus 3D. Total number of rivets in the critical path are 3. Total number of rivets in the critical path are 3. B minus 3D. B minus 3D into thickness, that is 6, plus S square by 4G plus S square by 4G, because of 2 inclined lengths are there. One inclined length, second inclined length. 2 inclined lengths are there. So 2 inclined lengths are there. 2 times of S square by 4G into T. S, that is pitch, is given as 35 mm. G is given as 20 mm. G is equal to 20 mm, and staggered pitch is given as 35 mm. So you can easily calculate. Thickness is basically 6 mm. Thickness is basically 6 mm. Okay. Now we can also calculate the value by applying, this is basically the formula for the calculation of B net. We have to multiply this value by 150 megapascal. 150 megapascal. After calculation, I found the value of P is equal to 59.512 kilonewton. So my dear students, here in general, if I am talking about the minimum value 45, 52.6 and 59.512. So you can say our final shear capacity, that is the maximum tension is equal to, or maximum tension is equal to minimum of 45 kilonewton, 52.65 kilonewton and 59.512 kilonewton. So our minimum value is 45 kilonewton. So answer is 45 kilonewton. So nearest option to 45 kilonewton is 42.3 kilonewton is our answer, because we cannot round off to the maximum value, because by applying the more force, if we round off the value to the 52.65 kilonewton, that is the available option, then obviously the section may fail in shear. So this is our question number 26. Now let's move towards question number 27. A bracket. My dear students, this question is the same as we had discussed. So F1 we have to calculate, F2 we have to calculate, and FR, resultant, we have to calculate. This is the same thing basically. So you can calculate the value. I am just explaining only the answers. F1 will be 10 divided by 4. F1 will be 10 divided by 4. F2 will be P into E, 10 into 100 into radial distance of every rivet will be, or for every rivet will be 40 square plus 30 square whole under root. 40 square plus 30 square whole under root for every rivet. Okay, so here 40 square plus 30 square, that is 50 mm, whole divided by 4 times of 50 square, because 4 rivets are at the same level. F2 value, after calculation you find the value of F2 is equal to 5 kilonewton, F1 is equal to 2.5 kilonewton. So resultant force FR we have to calculate. F resultant will be equal to whole under root of 2.5 square plus 5 square plus 2 F1 F2 into cos theta. Now tangent of theta is equal to 30 divided by 40. Tangent of theta is equal to 30 divided by 40. From here theta is equal to, you can calculate the value of theta easily, and that is or theta is equal to cos theta. Initially directly calculate the value of cos theta. If hypotenuse is 50, this is 50, this is 40, this is 30, so cos theta will be equal to 40 by 50, that is base upon hypotenuse. Cos theta directly you can calculate cos theta. Okay, so that is 4 by 5, that is 4 by 5. After solution I found the value equals to 7.16 kilonewton. Same thing. Okay, here 4 bolts are there, that's why the applied force has been distributed in the 4 bolts. 10 mm diameter, no requirement. Supports a load of load is given, eccentricity is given. After making all the necessary arrangements, or after converting all the units, we find the value equal to 7.16 kilonewton. This is our 27th question. Now 28th question. A fillet weld joint of 6 mm size is shown in the figure. The welded surface meets 60 to 90 degree, means K value is equal to, here what is the meaning? K value is equal to 0.70. Permissible stress is 108 megapascal. Fs value, safe load we have to calculate, F value we have to calculate, and obviously the size of weld is given as 6 mm S. So my dear students, effective throat thickness is equal to 6 into 0.7, that is 4.2 mm. That is okay. Effective throat thickness, that is okay. Now length of weld is given 100 plus 50 plus 50. L is given, that is 100 plus 50 plus 100, that is 250 mm. That is 250 mm. Okay. So safe load we have to calculate. P safe is equal to L effective into effective throat thickness into the stress available, that is 108 megapascal. So the very simple problem is there. 4.2 into 250 into 108 into 10 to the power minus 3 for Newton to kilonewton. P safe is equal to 113.4 kilonewton is our answer. So our option number C is correct option, 113.4 kilonewton. That's okay. Very simple problem was there. Now let's move towards question number 29. A moment M has a magnitude of 50 kilonewton meter, means moment is also there. So column flange, it is bracketed by using 4 20 mm diameter rivets. Shear force induced in the rivets, and as we know that, my dear students, F2 value that we had discussed in our eccentric riveted connections. So F2 value can easily be calculated. F2 value can easily be calculated. Oh, that is equal to by the formula M into R into algebraic sum of all radial distances square. Yes or no? We had discussed. So a moment is 50 kilonewton meter. Here the moment is given 50 kilonewton meter. Newton to kilonewton 10 to power 3. Meter to mm 10 to power 3. So total multiplied power is 10 to power 6 into radial distance 50 plus 50, that is 50 under root of 2. Pythagoras theorem, 50 under root of 2. This radial distance I am talking about, from here to here, radial distance. This is our radial distance, whole divided by 4 times of radial distance is square. 50 into under root of 2 whole square. Basically you can say the radial distances are here. Likewise this is our radial distance r, radial distance r, radial distance r, radial distance r. All values are of 4 value r. Okay, now you can easily calculate the value of f2, and after calculation I found the value equals to that is final value is equal to 176.77 kilonewton is our answer. Okay, that is 29th question. Now let's move towards the question number 30. An Indian standard angle section 100 by 10 having the cross section something that is welded along A and B. Likewise this you can say heel of the angle, you can say toe of the angle, such that length of the weld A and B are L1 and L2 respectively. Now we have to calculate the value of the length of the weld. So my dear students, if I am making the diagram at this particular cross section, here the welding surface is L1 there, here the welding surface to the gusset plate L2 is there. This is our gusset plate. Okay, we have to calculate these lengths L1 and L2. So here basically longitudinal shear important role plays, P1, and here also P2. This is the type of the problem of the moment free connection. Basically this is the type of the moment free connection, and you need not to calculate the values because we have very simple fundamentals that we had discussed in our theoretical discussion. Center of gravity lies here. If CG lies here, then obviously P1 will be less as compared to the P2. P1 is always less as compared to P2, because if I am talking about a simply supported beam, if P is here, this is our L1, this is our L2. Now reaction will be P into L1 here, P into L1 divided by total L, and here P into L2 divided by total L. Since L1 is more, then a reaction R2 will be more. Since L2 is less, reaction R1 is less. So here R1 is less than R2. Similar case is here. If this distance is less, let us suppose that this is our H1 fundamental, this is our H2 value. If H2 is more, here H2 is more, so as compared to, H2 is more as compared to H1, then obviously H1 is more, H1 is more as compared to H2, then obviously P1 will be less than P2. So corresponding to P1, L1 will be less than L2. That is okay. So from the options given, this option cannot be there, this option cannot be there, this option cannot be there, because length totally dependent upon the maximum force in the maximum longitudinal shear. These are the longitudinal shear in the weld material. This is also the longitudinal shear in the weld material. Longitudinal shear in weld material. Okay, so L1 will be less, so our option number A is correct option. Now let's move towards next 31st question. Maximum size of a weld for the square edge, and obviously my dear students, this is S maximum is equal to T minus 1.5 so square S and 3 by 4 for T minimum for rounded edge. This is for the rounded edge connection, and this is for the square edge connection. square edge connection. So here 1.5 less than, A option is correct, that is 1.5 mm less than the thickness of the plate. Now 32nd question is, one plate of size this 112 sorry is lapped joined another plate of size 200 by 12, okay, by a fillet weld of size 10 mm. Size of fillet weld is given as this one. Lap length is given. Fillet is provided on three sides of the smaller plates. Determine the, basically this connection is likewise this. This is our plate which has to be connected. This is our plate number 1. Now this has to be connected to another plate, plate number 2. This is our plate number 2, okay. This may be having a continuous length. This overlap is given here, here, here. This is limited to 100 mm. So we have to basically, this type of problem is generally, you can say, the slot welding problems are there, okay. Now total length is given. Effective length will be equal to, what will be the effective length? We have to calculate the maximum axial tensile force, that is L effective into effective throat thickness into the permissible stress. But for that we have to calculate the effective length of the weld. L effective is equal to 100 plus this dimension is 100 by 12. This dimension is 100 by 12 because plate number 1 is of the size 100 by 12. Plate number 2 is of the size 200 by 12. Okay. So L effective will be equal to L minus 2S, and L is equal to 100 plus 100 plus 100, that is 300 minus 2 times of size of weld is given as 10 mm, that is equal to 280 mm. L effective, that is okay. Angle to this and this plate is basically, you can say, a 90 degree. So for all the cases K value will be equal to 0.70. So effective throat thickness will be equal to 0.7 into 10, that is 7 mm. Now here F1 value is given. So we know the formula of permissible shear stress, that is 0.4 Fy, that is 0.40 into Fy is 250 megapascal, that is 100 megapascal, that is okay. Fs value we have. Now strength of weld we can easily calculate. Strength of weld we can easily calculate. The same formula, strength of weld, tensile strength. We have to calculate the value of the tensile strength. So the maximum axial tension we have to calculate. Axial, we need not to calculate the shear strength, because examiner asked us only to calculate the axial tension. Axial tension will be equal to 0.6 into Fy, sigma 80, 0.6 Fy. Effective length or plate is 100 into 12, that is equal to 180 kilonewton, that is equal to 180 kilonewton. Answer. But we also have to calculate the value of the shear strength. If strength of the weld is more than the axial tension, then we have to limit our value of the axial tension to that particular strength. So initially we also have to calculate the strength of the weld. So strength of the weld we also have to calculate. Strength of weld, that is effective throat thickness 7 into effective length 280 into 100 megapascal, that is 0.4 into Fy into 10 to the power minus 3. Now after calculation I found the value equals to 196 kilonewton. Now there are two questions. The first value is axial tension is this one 180 and strength of weld is 196 kilonewton. Since it is less than strength of the welded connections, since very important point is there that I am going to write down, since axial tension that is 180 kilonewton is less than the strength of weld, welded connection. Since it is less than strength of welded connection, therefore maximum axial tension, hence maximum axial tension, the joint will carry, maximum axial tension joint will carry is equal to 180 kilonewton. That is the minimum of two values, not the 196 kilonewton. Please be careful. Very important fundamental. So the answer of this particular question is 180 kilonewton. Answer of this particular question is 180 kilonewton. Okay, that's okay. So my dear students, these are the two questions are also remained. That is question number 33 and 34. Okay. Question number 33. Calculate the number of the bolts required at the end connections using the 20 mm diameter bolts. Allowable shear stress is given. Allowable bearing stress is given. So in general, we have to calculate the rivet value first, then the number of rivets. That's okay. That will be a very simple problem. Okay. Now let's calculate. Here we have to calculate the number of rivets. So before that, we have to calculate the rivet value, that is minimum of PS. Let's calculate the PS value. Since it is given, it is a double shear, so 2 pi by 4 into gross dia square, and 20 mm diameter bolts are given, so gross diameter will be 21.5. Gross diameter will be 21.5 into Fs is given, that is 80 megapascal. 80 into 10 to the power minus 3. After calculation, I found the value of PS is equal to 58.09 kilonewton. Now let's calculate the value of PB, that is equal to D into T, that is 21.5 into T minimum is 8, because gusset plate thickness is given, just only given, that is 8 mm, that is okay, into 250 into 10 to the power minus 3. 10 to the power minus 3. PB is equal to 43 kilonewton. PB is equal to 43 kilonewton. So rivet value will be minimum, that is equal to 43 kilonewton. Now since moment is not given, so number of rivets are subjected just only for force. Applied force is 240 kilonewton and force transmitted by, force resisted by one rivet is equal to 43 kilonewton. That is equal to 5.58, nearly equals to 6 numbers. Nearly equals to 6 numbers, that is okay. So this is our final answer. This is our final answer. 6 number of rivets are there. Okay. Now you can also calculate the value of the minimum pitch. Minimum pitch is equal to 2.5 times of nominal diameter, that is 20, that is 50 mm. This is the minimum pitch in between the rivets. That's okay. Okay, done. Now let's move towards our question number 34, the last question of the unit number 2, that is design of connections. Please be careful. Design of connections is very important unit for the GATE examination point of view. 34th question. A 12 mm bracket plate is connected to a column flange as shown in the figure. Okay. The bracket transmits a load of 200 kilonewton at an eccentricity E. Basically, this is out plane eccentric welded connections, from where eccentricity at extra are also measured from the CG of the rivet group or the weld group. 10 mm fillet weld is provided along AB, BC and CD. If eccentricity is given, verify the size of weld provided is adequate. Allowable shearing stress in the fillet weld can be taken equal to 108 megapascal. So we have to calculate, or we have to check down whether the size provided, that is this size, that is this 10 mm size, is adequate or not. Means this size of weld can resist the applied load or not, that we have to calculate, we have to check down. Okay. So my dear students, for this type of problem we have to calculate the value of F1, F2 and resultant stress. So here F1, this type of problem we had discussed in our theoretical discussion, don't worry. F1 is equal to force divided by effective area of the weld. Force is equal to here at 200 kilonewton into 10 to the power 3 whole divided by area of the weld will be AB plus BC plus CD, that is 600 plus 200 plus 200, that is 600 plus 200 plus 200, that is okay. Now this value is equal to 28.57 megapascal MPa. Basically here weld is treated as a channel that we had discussed in our out plane eccentric welded connections, yes or no? Channel. So we have to calculate all the properties in the same manner that we had discussed in our discussion of theoretical questions, and the critical location is taken here, A location is taken here. So here theta is this one, that is okay, theta is this one, and this value is given at 300 mm. This value is given as 300 mm. Okay, 300 mm. So for this particular you can say weld material, we have to provide the size of the weld. Now center of gravity initially we have to fix. All properties we learned how to calculate in our theoretical discussion. So from here x bar is equal to 40 mm. X bar is equal to 40 mm. So this, if this is 40 mm, so the remaining portion is 160 mm. Okay. So eccentricity can easily be calculated. Now second one is called as the torsional shear stress. F2 is equal to torsional shear stress, that is equal to T into R divided by IP. Yes or no? We had discussed or not? We had discussed. T into R divided by IP, polar moment of inertia, and R is this one, this radial distance R. This is our value of R. This is R. Okay. Now all the properties are calculated using the same thing that we had discussed in our theoretical portion. After putting all the values, I found the value equals to F2 is equal to small f2, in which we have to put the value of R, T and each and every parameter. So let's calculate all the values first. So our F2 value will be 85.81 kilonewton per mm square, 85.81 81 megapascal. Just I am telling you the final answer of Ixx and Iyy every parameter, in which radial distance will be 340 mm. This is the final value. You can calculate easily by the same fashion as we had discussed in the outplane eccentric welded connections. Ip, that is the polar moment of inertia, that is Ixx plus Iyy, and Ixx was 387 into 10 to power 6 into 10 to power 6 plus Iyy is equal to 26.13 into 10 to the power 6. So the polar moment of inertia can easily be calculated by adding these two values. Torsional moment, T is equal to, in general, F into E. F is 200 into 10 to the power 3 into eccentricity is, that is equal to 350 plus 160. 350 plus 160. This eccentricity is given as 350 mm. This eccentricity is given in the problem 350 mm. So the total eccentricity from the CG of the weld group will be 350 plus 160 mm, and from where 160 mm comes, this value is 160 mm. Okay, after calculation of the center of the gravity, after calculation of center of gravity, this value comes. Okay, 350 plus 160 mm. Now T value is equal to 102.10 to the power 6, 102 kilonewton meter. Okay, now you have all three values R, IP and T. You can put the values here, T, R and IP. F2 value is calculated 85.81 megapascal. F1 was calculated 28.57 megapascal. Now it's simple to calculate the value of the theta and at extra. So let's calculate the value of theta. Let us suppose that, my dear students, this is our welded material in the form of a channel, from where it lies, CGO lies here. This value is 160. This value is 160. Radial distance is 340. Yes or no? 340. And this value is 300. This value is 300 mm. So cos theta actually we have required. Cos theta is equal to base upon hypotenuse, that is 160 upon hypotenuse is a radial distance, that is 340. So cos theta base upon hypotenuse 160 over hypotenuse is 340. Now we have all the values. Now resultant stress, F resultant will be equal to whole under root of F1, that is was 28.57 plus 85.81 plus 2 times of 28.57 85.81 into cos theta, and cos theta is equal to 16 by 34, 16 divided by 34 whole under root. So from here you can calculate the value of resultant stress is equal to 102.39 megapascal. 39 megapascal means this kind of this type of the weld, this size of the weld can resist easily the 102.39 megapascal. F resultant. Permissible stress is 108 megapascal. Means this size weld can permit, since F permissible is more than F resultant, that is 108 megapascal is more than 102.39 megapascal. That's why you can say the size of the weld provided is adequate. That's why size of weld provided is adequate. That's okay. Okay. So my dear students, this was our question number 34, in which we have to verify the size of weld provided is adequate or not adequate. Okay, and we found that this size can easily resist the resultant stress of 102.39 megapascal, which is less than the permissible values. So you can say this size of weld even can permit the more value of the stress in the weld material. So this is safe or this is adequate. So my dear students, let's move towards the questions of next unit, that is the design of tension members. So let's start the question of design of tension members. So our first question of design of tension member is the net effective cross section area calculated in the steel angle tension member accounts for, means for a net cross section area, which one is applicable? As we know that A net is equal to basically gross area minus area of the bolt holes for tension members. So our A net is equal to A gross minus area of rivet holes or area of bolt holes, area of bolt or rivet holes. So here option number A is correct, that is the net effective cross section area accounts for tensile force, that is you can say the gross area basically, and the bolt holes Okay, now second question is, in the design of welded tension members, consider the following statement: the entire cross section area of the connected leg is assumed to be contribute to the effective area in the case of the angles. Obviously it is okay, because A1 is equal to, or A net is equal to, A net is generally equals to A1 plus KA2. Yes or no? We had discussed or not in our theoretical discussion? Yes. So A1 is the gross area of the connected leg, net area of the connected leg, net area of connected leg, because rivet holes are deducted, but this is the gross area of no deduction is there. So gross area of unconnected leg. Now this K parameter is used to consider the effect of the gross area to be more effective. So K is a factor basically that depends on 3A1 by 3A1 plus A2. Yes or no? A1 or 5A1 by 5A1 plus A2, 5A1 by 5A1 plus A2, and it is basically generally decided by shear leg effect. K is generally decided by the shear leg effect. Now second is, two angles back to back and tack riveted as per the Codal requirements may be assumed to behave as a T section. Obviously, likewise this is our gusset plate. To this gusset plate, this is one angle, this is one angle. So this kind of connections are behaved as a T section. This kind of connection is behaved as a T section. That's okay. So statement number 1 is okay. Statement number 2 is also okay. Check on slenderness ratio may be necessary in some cases. Not in some cases, but all the cases. Slenderness ratio check may also be there. We had design various questions for which lambda is equal to 180 or 350 or 250. That depends upon whether we have considered the secondary effect or not, the live load effect or not, wind effect or not. That is, so this is also okay. So our D option is correct. That is 1, 2 and 3 are the correct statements. Okay. Now our question number 3. Two angles 100 mm by 100 mm ISA and thickness 10 mm are placed back to back and connected to either side of the gusset plate through a single row 16 mm diameter rivets. So here basically area of connected leg and rivets are subject to double shear. It means basically, what is the meaning of this one? If angles are not tack riveted, please be careful. In the complete question, no tack word is used. So they behave as a, or they will behave as a single angle. So area of connected leg we have to calculate, and that is given as area of connected leg as 775 and area of unconnected leg as 950 mm square. So before starting the solution of this question, I want to write down one important note. One important note: if angles are not tack riveted, if angles are not tack riveted, they will behave as a single angle. They will behave as a single angle connected to the gusset plate. Please be careful. Connected to gusset plate means they will not behave as a combined unit. They will not behave as a combined unit. So in general, the total area, effective area of the pair of angles, so effective area of pair of angles is equal to 2 times of A net of each angle. Please be careful, very important fundamental is there. Now A1 is given as 775, A2 is given as 950, but they will behave as a single angle. That's why A net is equal to, that's why A net for every angle is equal to A1 775 plus K into A2, that is a 950. But K is here, since they act as a single angle, 3A1 by 3A1 plus A2. We have the values of A1 and A2. After putting the values, I found the value equals to 0.71. This is due to the more shear lag effect. More shear lag is there, less value of K is there. So net effective area after putting the value of K equals to 0.71. I found the value of A net is equal to, 1449.43 mm square. Now effective area of the pair of angle is equal to 2 times of A net. 2 times of A net. So you can say this value is equal to, here the value is equal to 2 times of 1449.43, that is equal to 2899 mm square is our answer. So our option number C is correct. Here angles are not tack riveted, it is clearly mentioned, please be careful. So this is our final answer of this particular question. Now next question, question number 4 is, the truss tie consisting of 4 and 5 are the basically a pair of a question generally consisting of ISA 75 by 75 by 8 and carries a pull of 150 kN. Likewise this is our gusset plate. This is our gusset plate. To this gusset plate angles are connected. Likewise this, to this gusset plate angles are connected likewise this. Okay, and here it is connected using some number of rivets, maybe any kind of the number of rivets may be there. So this is basically two angle sections are there. So 2 ISA 75 by 75 by 8, 2 ISA 75 by 75 by 8. This is our gusset plate. This is our gusset plate. Okay, now it carries a pull of, means here pull force is there. P is 150 kilonewton. At the end, two angles are connected, one each on either side of a 10 mm thick gusset plate. This is this gusset plate is 10 mm thick. This gusset plate is 10 mm thick by 18 mm diameter rivets arranged in one row, means our gross diameter D will be equal to 19.5 mm, because 18 plus 1.5 mm gross diameter is there. That's okay. Now allowable stress are given, maximum tensile force we have to calculate, minimum number of rivets we have to calculate, means rivet value is required before that. Okay, so for that initially we have to calculate the A net value, A1 and A2 or and whatever, because they are individual angles, that's why they are not tack riveted, that's why they act as a single angle section. So likewise this A net is equal to A1 plus KA2, and K, because they are not tack riveted, K equals to 3A1 divided by 3A1 plus A2 plus A2. Okay, that is okay. This is our final value. Now before that, A1 and A2 needs to be calculated. A1 and A2 needs to be calculated. This is our gusset plate to which every angle placed back to back. Likewise this, likewise this, and this is our rivet holes. Number of rivets are arranged in such a manner. So A1 is the area of this leg and A2 is the area of this leg. Now let's make the diagram. So this is our one leg and this is our second leg. This is our second leg. So one area is common for both the legs, this area that we had calculated in various numericals during our theoretical discussion. This is 75, this is 75, this is 8, and this is also 8. Okay, here also one deduction is also there. That deduction is 19.5 mm. That deduction is 19.5 mm deduction is there. Okay, now A1 needs to be calculated separately and A2 needs to be calculated separately. A1 will be equal to 75 minus 8 half minus 19.5 into thickness is 8. Similarly, A2 is equal to 75 minus 8 by 2 into thickness is 8. Thickness is 8. So A1 and A2, A1 is 412, A1 is 412 mm square, and A2 is 568 mm square. That's okay. Now we have to calculate the value of A net first. A net is equal to A1 plus K. After putting the value of A1 and A2, I found the value of K is equal to 0.685. So plus 0.685 into 568, that is equal to A net is equal to 801.2 16 mm square. Please be careful, this is the area of one angle section, but the tie member acts as with the help of two angle sections likewise this. That is initially given. Okay, so effective area of tie is equal to effective area of tie is equal to 2 times of 801 into is equal to 2 times of so the value is 2 into 801.16, that is equal to 10.32 mm square. That is okay. Now maximum tensile load initially we have to calculate. Maximum tensile load, fourth question. Solution of question number 4 is maximum tensile load is equal to per unit area in the tensile member, that is equal to load per unit area, maximum tensile stress. Maximum tensile stress is equal to load is equal to given as 150 kilonewton 10 to power 3 whole divided by area is 1602.32 1602.32, that is equal to 93.6 megapascal. That is answer. So our option number A is correct. Question number 4 is okay. That's okay. Question number 4 is okay. Now question number 5. Minimum number of rivets required, but minimum number of rivets are calculated on the basis of the rivet value. Initially we have to calculate the rivet value, since in this particular diagram rivets are subjected to double shear. Here one shear, one shear. So now let's solve the question number 5. Let's solve the question number 5. So rivet value initially we have to calculate. The gross diameter is 19.5 mm, that is okay. So rivet value we have to calculate. Rivet value is equal to minimum of PS and PB. PS is equal to 2 shear, 2 for double shear, pi by 4 gross dia square, and Fs is given as in the exam problem, Fs is given as 90 megapascal and FB is given as 250 megapascal. So 90 into 10 to the power minus 3. PS is equal to whatever the value is, that is 53.76 kilonewton. Okay. Now PB value, that is DT gross area into T minimum. T minimum in the problem that is given at 10 mm or 8 mm, but 8 mm two angles are connected, so 8 plus 8 that is 16 and 10, so T minimum is taken minimum of here T minimum is equal to minimum of, since it is a double cover board joint, so 8 plus 8 or 10, whichever is minimum. So our final value is 10 mm. Adopted value is 10 mm. So here 10 value is adopted into 10 into whatever the value is given 250 into 10 to the power minus 3. So after calculation I found the value of PB is equal to 48.75 kilonewton. That is okay. So our minimum value is 48.75 kilonewton. Rivet value is okay. Now number of rivets required N, applied force is 150 kilonewton and force shared by each rivet is 48.75. So minimum number of rivets are 3.077. Round off to 4 numbers. Round off to 4 numbers. So my dear student, this is like our question number 5, in which we have to calculate the number of rivets. So our answer C is correct. Answer C is correct. So here we have to make the diagram 4 number of rivets. 1, 2, 3, 4. So minimum pitch, you can easily calculate the value of the minimum pitch. You can easily calculate the value of minimum pitch, that is this one. This value shall be 2.5 times of nominal diameter, that is 18 mm. So this is 45 mm. This is 45 mm. That is the minimum pitch value. Okay. So please note it down fast. After that we will discuss the next questions, though, that are the design of compression members questions. Please note it down very fast. So let's start the questions of design of compression members. A steel column is restrained against both translation and rotation. At one end, means a fixed end is there, and second one is it is sorry, restrained against only rotation but free to translate at the other end. Means one end is fixed, another end is hinged. One end is fixed, another end is hinged. So here in general case the L value, effective length is equal to L. Effective length is equal to L, but sometimes the case looks like this way. So sometimes this is 1.2 L. So here option maybe C or maybe D. Both options are correct. Both options are correct. But most appropriate option is D option. Most appropriate option is D option. Okay. Now let's start the question number 2. So our question number 2 is a square root of a ratio of the moment of inertia to the cross section area. That is a simple question. That is R minimum value, minimum radius of gyration, R minimum radius of gyration. Radius of gyration is also called as radius of rotation, radius of revolution, etc. That is equal to under root of I by A. Okay. So option number D is correct. Question number 3 is, in the design of lacing systems, the maximum allowable slenderness, for the complete lacing system, the maximum slenderness ratio, lambda maximum for the lacing bar was, lambda maximum for lacing member was 145. So option number B is correct. Question number 4, the effective length of circular electric pole. So electric pole is fixed at the bottom and electric pole is fixed at the bottom and free at the this end, particular end. So here the effective length becomes basically a 2L. Effective length becomes 2L. L effective is equal to 2 times of L. So option number D is correct. Okay. Now question number 5. In IS 800 1984, the permissible compressive stress is based upon, on the basis of the working stress method, that was based upon the, you can say, Rankine Merchant theory. However, for 2007, it was based upon the, you can say, the Perry-Robertson formula. So working stress method code, that is 800 1984 code, it was basically Rankine Merchant theory. Rankine Merchant formula. However, limit states method code, that is 800 2007, it was based upon Perry-Robertson formula. Perry-Robertson's formula. Perry-Robertson formula. So here working stress method is asked. So Rankine-Merchant theory is used. Okay. Now, as per IS code number 800/1984, maximum allowable slenderness ratio for members carrying forces resulting from dead end and superimposed load. So option number A is correct because direct for lambda maximum for compression members is 180 because high chances of buckling are there. Pure compression members. However, for pure tension members, this value is 400. Lambda maximum is equal to 400. It is for pure tension members, and if it becomes more than 400, then the tension member behave as a cable, because less value is allowed because of high chances of buckling. Less value is allowed because of high chances of buckling. High chances of buckling are there in the case of the pure compression members. Okay. Now, the critical bending compressive stress in the extreme fiber. This is a 2020 exam question. GATE 2020 exam question. The critical bending compressive stress in extreme fiber of the structural section is 1000 megapascal. So here FCC is given as 1000 megapascal. It is given that the yield strength of the section Fy is equal to 250 megapascal. Width of flange is 250 mm. Thickness of flange is this one. Non-dimensional slenderness ratio lambda is equal to non-dimensional slenderness ratio that is used in Perry-Robertson formula, Fy by FCC whole under root. So whole under root of Fy is 250, FSCC is equal to 1000, 1 by 4, 1 by 2, that is equal to 0.5. Very important question is there, 0.50. So option number A is correct. This type of question may be asked in your future exams. Now next question. As per IS 800, effective length of a column effectively held in position at the both ends but not restrained against the rotation, means rotation is permissible. If rotation is permissible, both hands are hinged in general. So here both hands are hinged, and you can say likewise this, since both hands are hinged. So effective length of a general case is to be taken greater than ideal condition. True statements are, in general, here you can say one statement is typing mistake is there. The statement is, second statement is, I am this is our statement number 1. Now statement number 2 is, as per IS code number I am dictating, you can write down the statement number 2. The permissible stress in bending, compression depends upon Euler's buckling stress, and yield stress of steel. Now statement number 3 is also given. Effective length of column effectively held is greater than in ideal conditions. Three statement is not okay. So we have to find out the true statements. The true statements are, we have to calculate the true statements. Only 1 and 2 statements are true. This is our first statement. Effective length of column effectively held in position both hand but not restrained in rotation is taken to be greater than that ideal condition. That is okay because of we cannot maintain the perfect fixity. That is, we cannot maintain perfect fixity. Perfect fixity, that's why more value has to be taken, and this is okay. Obviously bending compression FCC depends upon, that is pi square E by lambda square, pi square E by lambda square. So Euler buckling stress as well as the yield stress of the steel, because lambda depends upon the Fy and FCC. Lambda depends upon under root of Fy by FCC. Okay, that is the final value. Okay, now here option number 1 and 2 both are correct. Two statements are 1 and 2 both are correct. Okay, please note it down very fast. After that we will move towards the questions of next chapter, that is beams. Next chapter, that is beams. Please note it down very fast. Design of beams. Let's start the question of design of the beams. Okay, now let's start the questions of design of the beams. First question is, assuming that there is no possibility of shear buckling in the web, means buckling of web is not there. It is assumption. The maximum reduction permissible by permitted by is odd number. Design bending strength semi-compact steel section. So basically no reduction is there, zero reduction is there. However, reduction was there in the case of the high shear, that is 0.6 Vs. That is the same, that is a different thing, but here no reduction is there, since it is governed by the, you can say, no possibility of shear buckling of the web. No possibility of shear buckling of web, zero, and because of no possibility of shear buckling, no possibility of buckling of web, no possibility of buckling of web. Okay. Now second question. The semi-compact section of a laterally unsupported steel beam has an elastic section modulus, plastic section modulus, and design bending compressive strength, that is ZE is given as 500 centimeter cube, ZP is equal to 650 centimeter cube, and design bending compressive stress sigma BC, that is 200 megapascal Newton per mm square. Okay, so we have to calculate the design flexural capacity. That simple formula is there. So design flexural capacity, design flexural capacity, because here section is semi-compact section. Here section is semi-compact section, so you can say till the time it is not reached to the plastic state, it is in the elastic zone only. It is in the elastic zone only. So due to the semi-compact section, design flexural capacity of semi-compact section. However, it is, if it is asked to calculate the design flexural capacity of the compact section, or you can say the plastic section, then you have to use the ZP value, but semi-compact section. But here it is not asked. Here it is asked just only to calculate the flexural capacity of the semi-compact section. That's why ZE is multiplied, not the ZP. ZE into sigma BC. So that is equal to 500 into sigma BC is 200 megapascal. Let's balance the units. Here centimeter cube is there. Here Newton per mm square is there. Newton per mm square is there. So this is you can say, for example, let's calculate the value. We have to calculate the design capacity, maybe Newton mm maybe. So 1 centimeter is equal to 10 mm. So that is 10 to the power 3 mm cube Newton per mm square. So this is cancelled out. So Newton mm. So multiplied by 10 to the power 3 Newton mm. Okay, that is our final answer. So value is 100. Convert the value into kilonewton meter. 100 kilonewton meter is our answer final. So this value is in 100 kilonewton meter is asked. So our value is 100 kilonewton meter. Value is 100 kilonewton meter is our answer. Okay, second question. Now third question. A steel beam supporting the loads from the floor slab as well as from the wall is termed as. Obviously, this type of question I had discussed with you people very clearly in our theoretical discussion. The beam was called as the spandrel beam. The floor beam projecting outside, or the beam projecting outside the floor. The beam projecting outside the floor level or floor wall is called as the spandrel beam. This type of question I had discussed with you people during our theoretical discussion, don't worry. Okay, now question number 4. Allowable average shear stress in unstiffened web for the beams made of the grade. Obviously, tau average is equal to 0.4 Fy. Very simple formula is there, because there are no chances of the buckling of the web. 0.4 into 250 megapascal, that is equal to 100 megapascal. So our answer is 100 megapascal. Okay, now let's move towards the question number 5. That is, an unstiffened web I section is fabricated from 10 mm thick plates by fillet welding as shown in the figure. Means 3 plates have been joined. This is 1 plate, this is 2 plate, this is 3 plate. These 3 plates has been joined. This is R1, this is 2, this is 3, using the fillet weld. Okay, now this thickness is given as 10 mm thickness. Every thickness is given as 10 mm. Okay, now we have to calculate the maximum shear load that can take. So maximum shear we can calculate. We have to calculate the value of maximum shear load. So shear load capacity of a section is generally given by the shear area multiplied by the shear stress. So shear load capacity of a section is equal to the area, that is 300 by 10 shear load, because we had discussed for all calculation purposes depth of web is taken as the overall depth. We had discussed, because it is assumed that entire shear force is to be taken by the web only. That's why for only for calculation purposes, you can say depth of web is equal to the overall depth. Depth of web is equal to overall depth, because most of the shear force, 95% of the shear force has to be registered by the web only. So shear load capacity is equal to 300 into 10, because most of the shear section has to be registered by this particular portion, this hedged portion, into what is the shear stress, that is 0.4 Fy. So 0.4 into 100. So after calculation, total value, I found the value as 300 kilonewton. After converting all the values, I found the value equals to 300 kilonewton. That is okay. So our answer is D option is correct. D option is correct. Depth of web is equal to overall depth, because most of the shear force is taken by web only. Most of the shear force is taken by web only. That's why for all the calculation purposes, depth of web is equal to the overall depth. Okay, now let's move towards the question number 6. Question number 6 is an ISMC 400 with a flange width of 140. It's subjected to an axial compressive load of this one. So actually, let us suppose that this is our slab base. This is our slab base. This type of question also we had discussed. and here basically a channel section is there, sorry, an I section is there, having the overall depth is equal to 400 mm. Okay, now this is the width that we have to design, and this is the length of the slab base, So in general, my dear students, we have to fix the value of A and B because they're the extreme fiber distances A, and this value is basically small b. Since in the question A and B are equal, so A is equal to, in general, initially we have to calculate the value of the size of the slab base. So design the slab base resting on the concrete grade M15. M15 means you can say FBR, that is the bearing stress, is equal to maximum shear is 0.45 FCK. So 0.45 into FCK concrete 15 megapascal. So value is 6.75 megapascal. So that's why we can calculate the required area. Required area is equal to how much value? The load applied is 750 kilonewton. Into 10 to the power 3 whole divided by 6.75 Newton per mm square. So value is equal to 1.11 into 10 to the power 5 mm square. So required area is this one. You can assume any kind of the base of the slab size. Consider slab base of size, let us assume 600 by 350 by 20 mm thickness. However, it is a very heavy plate, but we have to assume. Okay, so here A and B initially we have to calculate. A is equal to 600 minus 400 divided by 2, that is 100 mm. Similarly, small b is equal to 350 because this dimension we have assumed 350 and this dimension we have assumed 600. Okay, 350 minus 400, sorry, 350 minus this flange width is given as 140 mm in the question. This is given as 140 mm. So 140 whole divided by 2. 140 whole divided by 2. So B is equal to you can say 105 mm. 105 mm. So here A and B are we have calculated. A is equal to 105 and B is equal to 100 mm. But this A and B we can replace. The larger dimension is taken as A. That is 105 mm for all calculation purposes, for minimizing the effect of the thickness of the base plate, and smaller dimension is taken as 100 mm. That is we had discussed in our theoretical portion. Please be careful. So minimum thickness of the base plate initially we have to define. So let us suppose that thickness of the base plate when the loading is concentric, then thickness in mm is given as whole under root of 3w by sigma bs, 3w by sigma bs. Sigma bs is the bearing stress. A square minus b square by 4. A square minus b square divided by 4. Okay, now what is the net upward soil pressure? That is an important fundamental. Net upward soil pressure, that is an important fundamental. Very important condition is there. So that is equal to, here W is not given, but net upward soil pressure is in general is calculated. W is calculated separately. W is equal to, what is the load? Load is 750 into 10 to the power 3 whole divided by area of the base plate that is provided, and base plate is provided as 600 by 350 size. So net upward soil pressure, net upward soil pressure, that depends upon the grade of concrete also, that is equal to 3.57 megapascal. However, it is also calculated net upward soil pressure, that is equal to FCK divided by factor of safety of 4, that is equal to 15 by 4, that is also the nearly same value. This is another alternative to calculate the net upward soil pressure when the area of the base plate is not given to you. Now this is net upward soil pressure if area is fixed, 3.75 megapascal. Okay, now thickness of minimum base plate, if sigma bs is not given, you have to assume sigma bs value 185 megapascal. Bearing stress in the slab base, that is 185 megapascal if it is not given. Okay, so 3w whole under root of 3, w is 3.57 whole divided by this is 3.57 whole divided by 185 into a square is 105 whole square minus b square divided by 4, and that is equal to thickness minimum base plate is equal to 22.21 mm, that is more than 20 mm. So we can say that the size which we had selected is not applicable in this particular case, because 600 by 350 by 20 is not applicable because this is failed. So we can adopt this size. That is 650 by 325 by 20 mm. That is okay because it is somewhat more, just somewhat more than the 20 mm thickness, and hence this section is failed. 600 by 350 by 20 mm is not adequate. So we can use, hence section used is you can say 650 by 325 by 28 mm. Hence 650 by 325 by 28 mm is the best suitable section, for the given loading conditions. That's okay. Now let's move towards this is please note it down very fast. This is question number 6, design of the base plate. Okay, now let's move towards the questions of unit number next, that is design of plate girders, gantry girders, industrial roofs, etc. we will discuss. So now let's discuss the questions of unit number 6, that is plate girders, gantry girders and industrial buildings. Okay, so our first question is, in a plate girder the web plate is connected by the flange plates by fillet welding. The size of fillet is designed to safely resist, obviously the size of fillet weld is designed to safely resist the horizontal shear force between the flanges and the web plates, obviously, because the horizontal shear force is the important fundamental. So our option number basically C is correct option, because it is designed to resist the horizontal shear force. Likewise, this, if 3 plates has to be joined for making this type of all the fundamentals we had cleared during our theoretical discussion. Okay, here fillet weld was applied, here fillet weld was applied. Okay, so basically these are designed to resist the horizontal shear force in between the flanges and the web plate. Okay, now, or you can say to prevent the, you can say to prevent the movement of the flanges and the web in between the joints. These are the cover plates that initially we had required. Sorry. Question number 2. Which one of the following element is in a pitched steel roof, industrial roofs, primarily resist the lateral load parallel to the ridge? In general, my dear students, bracing members are used. Bracing members are used that we had discussed during our theoretical discussion to resist the or because they are main members, purlins वगैरह at extra purlins at extra are not designed to resist the parallel loads. Designed the parallel loads. So for that, our bracings are used. So for that, our bracings are used. Bracings may be the cross bracings, may be the lateral bracings. These members, yellow color members are the bracing members. These yellow color members are the bracing members. Okay, my dear students. So these members may be used to resist the applied load. These members may be used to resist the applied loads. So option number A is correct. Okay, bracing members are generally used. Okay, now question number 3. The maximum permissible deflection for a gantry girder over the 6 meter span electrical overhead traveling crane, EOT crane. So my dear students, up to 500 capacity, up to 500 kilonewton capacity of EOT crane, as we know that span divided by 500 or span divided by 750, span divided by 750 is the maximum deflection in the gantry girder. Delta maximum in gantry girder. Okay, so span is given as 6 meter. 6 meter means 6000 mm divided by 750. So value is equal to 8 mm. Value is equal to 8 mm. Let's calculate also. That is 600 divided by 750. That is equal to 8. Okay. So my dear students, question number 4th is effective length of a rafter between two nodes at a distance perpendicular to the plane of truss. So my dear students, when the perpendicular to the plane of trusses are there, then effective length is equal to basically perpendicular to the plane of truss, that is effective length becomes equals to 0.85 L. That these basically, my dear students, these concepts I had discussed with you people during our theoretical portion very clearly. That's why I have marked directly the answers. Okay, 0.85 L. Now last question of this particular unit, that is plate girder, gantry girders and the industrial roofs, is question number 5. The cross section of a simply supported beam plate girder is shown in the figure. Loading on the girder is symmetrical. The bearing stiffeners are provided. Sole means of the providing restraints against the torsion, means only the stiffeners are the meaning. Then these only when the stiffeners are the meaning, then some important criteria I had discussed with you people, that is LS value. If only the stiffeners are the criterias, then LS value, length of the stiffener, shall always be more than or equal to 0. This concept we had discussed basically, alpha S into d cube T thickness of the compression flange. Thickness of compression flange. Thickness of compression flange. Okay, my dear students. So LS value, this one. So alpha S is basically here a 0 value because and there is not applicable in this particular case. So alpha S value is basically different values are there. Different values are there. So for that, because alpha value is generally lies from 0.00 to 0.006, alpha S lies in between 0.0 to 0.006. okay, that depends upon basically KL divided by R minimum. that depends upon KL by RY, effective length by RY. If it is less than equal to 50, this value is equal to alpha value is equal to 6. This value is 0 for general cases, and basically if it is less than 50, or my mistake, 0.006 sorry, and alpha is equal to 30 KLRY square. Alpha is equal to, this is 30 divided by KL by RY whole square for KL by RY more than 100. KL by RY more than 100. This is the value of alpha. This is the different values of alpha. Okay, but here just only this value is applicable because KL by RY is less than 50 mm. Less than 50 mm, this value is applicable. So alpha is okay. Now we can calculate the value of LS, that is 0.7534 alpha S d cube T, thickness of the compression flange. Thickness of the compression flange. So thickness of compression flange is given here, that is TCF is equal to 25 mm. TCF, that is 25 mm, that is okay. Okay, so LS we can easily calculate. LS is equal to more than or equal to 0.34 into alpha is 0.006 into D cube over all D. Overall D is 1445 plus 25 plus 20, that is 14 you can say 1490 mm. 1445 25 and this is 1470 1490. Okay, so this total value is 1490 mm. Okay, so 1490 to the power 3 into thickness is given as 25. So this is more than or equal to 168.70 into 10 to the power 6 mm to the power 4. Now you can provide a flat. Now you can provide a flat section, and flat section available are 250 into 25 into 250 into 32, 228, 232. Now let's try 200 by 32 because length is applicable likewise this one. Okay, so provide on both sides of the stiffeners. So therefore provide 200 by 32 mm flat on both sides of web plate, for bearing stiffeners, as shown in the figure. Likewise, this is our one stiffener is there. So here we have to provide on both the sides of this stiffener as a flat. So this value is 200, this value is 200, and thickness is 32. Okay, now this is the basic function of the stiffener. Okay, now IS value of this particular arrangement we have to calculate separately. IS value we have to calculate separately. This is basically IS value, my mistake. Moment of inertia of the stiffener. Okay, IS. So for the arrangement, IS value we have to calculate. For this arrangement, IS is equal to, obviously, 3 rectangular plates are there, 1, 2 and 3. So 2 times of 32 as it is, opposite dimension cube by 12, 200 cube by 12 plus you can say parallel axis theorem is applied. 32 into A into R square into R is and 200 half plus 8 half, 200 half plus 8 half whole square, r square. Okay, now this value for the stiffeners, because only these flats are used as a bearing stiffeners, so this value is equal to 181.11 into 10 to the power 6 mm to the power 4. So my dear students, the moment of inertia of the stiffener which we had provided as a bearing stiffener is 181.11 into 10 to the power 6 mm to the power 4, which is more than 168.70. that is required. Moment of inertia of the stiffener required was 168.70 into 10 to the power 6 mm to the power 4. That is okay, because we had provided a stiffener which is having the more moment of inertia as compared to the required moment of inertia according to the given conditions. So this is our question number 5. Please note it down very fast. After that we will discuss the questions of the plastic analysis, that is unit number 7. So let's start with the questions of the plastic analysis of the beams and frames, unit number 7. Please note it down very fast. So now let's discuss the questions of plastic analysis of beams and frames. So our first question is, match the information group given in the group 1 and group 2 factor to decrease the ultimate design strength to the design strength, that is obviously called as the factor of safety. So, or you can say partial factor of safety, material partial factor. So factor to increase working load to the ultimate load, that is equal to the load factor, obviously that is equal to the load factor. So statistical method means you can say the statistical method is the lower bound theorem and the kinematic theorem is equal to the upper bound theorem. So P3Q4 R2S1. So our option number C is correct. Okay, now next question. The ultimate collapse load in terms of plastic moment capacity by kinematic approach for a curved cantilever beam. This type of question I had discussed with you people directly, and our answer was 6 MP by L. Yes or no? We had discussed. By principle of virtual work done, initially we have to make the collapse bending moment diagram. Plastic hinge will be developed here and under the load. This is theta, since of the this is also theta because length is equal. Okay, length is equal. So MP moment is here required to rotate. MP moment is required here. So in general, this value is equal to L by 2 into theta. As per principle of virtual work done. Internal work done, that is done by MP moment, must be equal to external work done. Okay. So internal work done is equal to MP into theta plus MP into theta plus theta. Here MP into theta plus theta. So 2 MP into theta must be equal to PU into L by 2 load into displacement, PU L by 2 into theta. So PU is equal to 6 MP by L. That is our correct option. Okay. Now question number 3. As per IS code number 2008-2007, the cross section in which extreme fiber cannot reach the yield stress, means it fails before the yield stress, that are called as the basically semi-compact sections, but cannot develop the plastic moment capacity due to failure by local buckling. These sections are called as the semi-compact sections. This definition I had discussed with you people during the discussion of the plastic analysis of beams and frames. Okay. In the theory of the plastic bending of the beam, ratio of the plastic moment to the yield moment, MP over My is equal to the safe factor. MP over My is equal to the safe factor. Okay, so option number A is correct. Now question number 5. The shape of a cross section which has the largest shape factor. Largest shape factor is for the 2.34 for the basically 2.34 for you can say triangular section, but triangular section is not given here. Diamond section 2.0, circular section 1.69, I section 1.14 to 1.12 to 1.14, diamond 2.0, diamond 2.0, solid circular 1.69, and this rectangular is 1.50. So our option number C is correct. Diamond section. Diamond section. A cantilever beam. This type of question I had discussed with you people. For the cantilever beam, we have to calculate the plastic hinge length. So plastic hinge length here was given by LP. LP is equal to, I had discussed the formula, L into 1 minus 1 by shape factor. LP into L into 1 minus 1 by shape factor. So let's analyze the situation. LP by L is equal to 1 minus 1 by F. So this is D option is correct. D option is correct. This type of question I had discussed with you people earlier very carefully in the theoretical discussion. Okay. The four cross sections shown below are required in increasing order of their respective shape factor. Which one of the following order is correct? So in the increasing order, the highest value is for the you can say diamond, then circular, then this is our first, this is our first, this is our second, this is our third, and this is our fourth. So 2 1 4 3, 2 1 4 3. So option number increasing order, my mistake, increasing order, the lowest value is 4, then 3, then 2, then 1, then 2, 4 3 1 2, 4 3 1 2. So here typing mistake is there, typing mistake is there. C option will be correct. 4 3 1 2. C option, please make the correction. 4 3 1 2 is option correct. Okay. The shape factor for the section, basically in the horizontal vertex. Here upward vertex is not there, here horizontal vertex is there. So for this type of sections 2.0 is there, and for the vertex upward 2.34 is there. So for this type of sections 2.0 shape factor is there, S is equal to 2.0. Now question number 9. For a fixed beam with span L having plastic moment capacity L, the ultimate center concentrated load. The fixed beam, this value we have to calculate, P U. So this type of question we had discussed. Here plastic moment is there, sorry, MP, here MP is there, and here also the MP moment is required. So this value is 8 MP by L. This type of question we had discussed, or directly you can easily calculate PU of a fixed beam is 2 times of PU for a simply supported beam, and PU for a simply supported beam was 4 MP by L, 4 MP by L, but here the value is 8 MP by L. Okay, so D option is correct. Now question number 10. For a propped cantilever beam, the same question is 6 MP by L is repeated. Actually this unit is having the highest weightage, that's why I have typed all the questions of the plastic analysis 6 MP by L. The T section, in the T section generally, in the case of plastic moment, neutral axis T beam subjected to plastic moment, neutral axis lies. Neutral axis is always basically you can say always in between ZZ and YY axis, because this is the neutral axis position. This is the neutral axis position. So neutral axis position always lies in between the YY and ZZ. We had discussed also a numerical of the T section on the basis of the some numerical values. Okay. Now 12th question. Which one of the following condition, both elastic and plastic method of analysis of indeterminate structure have to satisfy. Basically, we have four conditions. The which one of the following conditions, both elastic and plastic method of analysis have to satisfy: yield condition, that is must; mechanism, that is must; equilibrium, that is must. Yield must be there, mechanism must there, equilibrium must there, but compatibility condition need not be must. So which one of the following condition, both elastic and have not to satisfy, that is basically compatibility condition. Compatibility condition, force and displacement methods are used, that is moment distribution method, slope deflection method, Carnage method, three moment theorem, Calibration theorem. Both are the methods of the structural analysis. Basically compatibility of the deformations. 13th question. In the section shown in the figure, turns from fully elastic to fully plastic, depth of neutral axis decreases by, means basically initially we have to calculate the fully elastic case y bar for fully elastic case, for fully elastic case y bar, we have to apply the Varignon's theorem, 60 a1y1 plus a2y2 divided by a1 plus a2. a1 plus a2 is 60 into 5 the top fiber and 60 into 5 the bottom fiber, that's okay, into y bar is 5 half plus 60 into 5 into, and y bar is 5 plus 60 half. After calculation I found the value equals to 18.75 mm. 18.75 mm. So this y bar is equal to 18.75 mm for fully elastic section, but for fully plastic section, obviously the plastic neutral axis is that axis which divides the total area into two equal parts, two equal halves. So the fully elastic plastic neutral axis lies here, phi, because the above area is same, below area is same. Okay, so the difference is 18.75 minus 5, that is for fully plastic section the y bar is equal to equal area axis, that is equal to 5 mm. So neutral axis reduces by 18.75 minus 5, that is 13.75 mm. So answer is A option is correct. Neutral axis reduces by 13.75 mm. Okay, that's okay. Now question number 14. The dimensions of a symmetrical welded sections are shown in the figure. The plastic section modulus about the weaker axis. So in general you can say section modulus is generally refers to basically the flexural strength, and it is weaker against the flexural about the y axis. So as we know that ZP is equal to area divided by 2 into y1 bar plus y2 bar. Okay, but please be careful, plastic section modulus, y1 bar and y2 bar must be same. So basically you have to identify the area likewise this, the top area is there and the bottom area is there. So y1 bar and y2 bar initially we have to identify, that is after calculation I found the value y1 bar and y2 bar by using Varignon's theorem, a1 y1 a2 y2 divided by a1 plus a2 by Varignon's theorem, because this is a1, complete a1 is there, net center of gravity of this area y1 bar, net center of gravity of the bottom area is also y2 bar. Okay, now that is okay. Now total area is equal to, you can easily calculate, total area is equal to 149 plus that is 200 minus 9 and 9, that is 200 minus 9 and 9 that value is equal to 200 minus 18, that is 182 into 6.1 plus 140 into 9, that is okay. Total area is equal to whatever the area is 3630.33 mm square. Okay, that's okay. Now ZP can easily be calculated. ZP is equal to total area 3630.3 whole divided by 2. Y1 bar is 24.763 plus 24.763. This is also 24.763, and after calculating I found the value equals to 89.89 centimeter cube is our answer. Okay, so my dear students, here we have to calculated the y1 bar and y2 bar, then we had calculated the values. The ZP is 89.89 centimeter cube. Okay, now next question. The prismatic propped cantilever beam of span L, moment capacity MP, subjected to concentrated 6 MP by L, that is okay. So for this type of conditions 6 MP by L, so alpha value is 6, alpha value is 6 here, alpha is equal to 6 here. Okay, now the same question. A fixed end beam is subjected to concentrated load as shown in the figure. The beam has two different segments. This type of question we had discussed directly, and our option was 7 MP by L. Our option was 7 MP by L. Now let's here two mechanisms are there. Let's try all the mechanisms. Let's try all the mechanisms. Number one, the first possibility. Number one, the first possibility. In the first possibility, likewise, here the complete is assumed as a mechanism. Likewise, this complete is assumed as a mechanism. Here the plastic moment is there, plastic moment is there, and this type of behavior, plastic moment is there. So MP into theta, 2 MP theta, this is MP into theta, but both angles are different. Phi due to different length, this is phi and this is theta. MP, this type of question, all questions we had discussed. MP, okay, but here 2 MP is there. At the junction minimum value is taken. At this junction minimum value is taken, not the maximum value. So as per principle of virtual work done, in general, my dear students, 2 MP theta plus MP into phi plus MP into theta plus phi, that is equal to P into 2L by 3, 2L by 3 into theta, 2L by 3 into theta. So here P is equal to 8.25 MP by L. And what is the value of the phi? Basically theta is equal to 2 phi, because if this is 2L by 3, so this will be L by 3. Only then the length is equal to 2L. Only then the length is equal to 2L. Now the second mechanism, according to the second mechanism, we have to also calculate the value of second mechanism. Second possibility. Second possibility, if the concentrated load is there and the basically if likewise mechanism is developed likewise this, likewise this. Okay, so here 2 MP is there into theta. This is also a theta because a central concentrated load is there, and this is also MP because at the junction when two sections meets, the minimum value of MP is taken. This is theta, this is theta. So total MP into theta, 2 MP theta, MP into theta plus theta, total 5 MP into theta. 5 MP into theta is equal to P into 2L by 3 into theta. After solution I found the value is equal to Pu is equal to 7.5 MP by L. So answer is basically 7.5 MP by L because the minimum value of second and first possibility is the final value. So that is 7.5 MP by L. Now question number 17. A propped cantilever, vertical concentrated load mid span, plastic moment capacity, and obviously this question is repeated more and more times. 6 MP by L. A fixed beam subjected to load. Basically this is the same question as we had discussed. In the previous case we had discussed about the generally you can say propped cantilever. Now here it is fixed, and as we know that the value is 2 times of the either simply supported beams or the you can say the propped cantilever beam. So here Pu is equal to 2 times of 7.5 MP by L, that is final answer 15 MP by L. C option is correct. 15 MP by L, C option is correct. That is very important fundamental. Okay, please note it down very fast. 19th question. This is our 19th question. So our 19th question is for formation collapse mechanism. In the following figure, the minimum value of Pu is C MP by L. MP and 3 MP are the moment capacities. Same condition is there as it is condition is there as we had discussed in the previous question. So mechanism 1 and mechanism 2 will be formed. I am just telling you the answer of mechanism 1 and mechanism 2. You can calculate. If any doubt comes, you can ask me. Mechanism 1, the Pu value is equal to 24 MP by L, and in mechanism 2 Pu value is equal to 40 by MP by L, 40 MP by L. So load is smaller obtained out of these two mechanisms. Sorry, 40 by 3. This is my mistake. 40 by 3 MP by L. Here I have assumed the plastic hinge here, and under the load P. Okay. So here MP into theta plus theta because the symmetrical condition is there. Here 3 MP is required. Here MP is required. And in this particular case, we have assumed the situation likewise this. Here the central point and this value. Central point MP. This is 3 MP. This is MP. This is theta. This is theta. This is MP into theta plus theta, but load is acting here. Please be careful. So deflection is this one, that is you can say 1 MP, or you can say just only 1 divided by or L by 4 into theta, so whatever the value is there. Here the deflection is L by 4 into theta, and here the deflection is L by 2 into theta. You can equate the value using principle of virtual work for the external work done as well as the internal work done. So the correct value of Pu is minimum of these two values. So this is and C value is 40 by 3. That is 13.33 is our answer. Okay. 19th question is okay. Now 20th question. The same question is there, property cantilever beam is there. So our answer is 6 MP by L. Same question is there. Now 21st and 22nd question. For the beam, a propped cantilever beam is there. If P is 80 kilonewton, then reaction we have to calculate. This P is given as 80 kilonewton. This P is equal to 80 kilonewton. So let us suppose that this is reaction R. So you can easily calculate the value of a reaction, and net deflection at C must be equal to 0. Net deflection at C must be equal to, let us suppose this is A, this is B, because C balances the deflection. So net deflection at C must be equal to 0, obviously. This is from compatibility condition. Okay, so now let's balance the units. PL cube by 3EI, RL cube divided by 3EI minus load effect, that is PL cube by 3EI, P into 1.5 cube by 3EI minus PL square by 2EI into moment into L distance, PL square by 2EI, P 1.5 square divided by ML square by 2EI into L2 is also 1.5 is equal to 0. So from here our R value, after putting all the values, R value is equal to 25 kilonewton. Reaction value is equal to 25 kilonewton. Only just I have applied the net deflection at C is equal to 0. Delta at C is equal to 0. From compatibility condition we have found the value PLQ by 3i minus this P creates a moment about the C. That is anti-clockwise moment. That's why P into, or you can say this anti-clockwise moment is there, ML square by 2EI into L. So L is equal to 1.5 meter. And here L is equal to RL cube, that is for this value L is equal to 3 meter. Okay, now this is 25 kilonewton. Now if the magnitude of load P is increased till the collapse load, means if P value is increased to the collapse load, plastic moment capacity is 90 kilonewton meter. So for this particular condition, my dear students, MP is basically increased to 90 kilonewton meter. So here how many of the plastic hinges are formed? One there and one here. So this is MP into theta plus theta, this is MP into theta. So 3 MP into theta must be equal to P into, what will be the lateral deflection? 1.5. Let's make the collapse bending moment diagram. Let's make the collapse bending moment diagram. Here no plastic hinge is there, so no MP, this is theta, MP into theta. Okay, and here load is basically P, so this value is equal to 1.5 into theta. Okay, my dear students, so from here you can calculate the value of reaction. P is given as 180 because P is basically increased till the collapse load. Basically it is reached to the 180 megapascal or 180 value. So 3 MP theta, P into 1.5 theta, 3 into MP is 90 megapascal, 90 kilonewton meter. So P is equal to 180 kilonewton from this condition. But we have to determine the reaction value. That is R into 3. For this condition, summation of all the moments is equal to 0. R into 3 plus MP, because R gives me the clockwise, MP gives me the clockwise. This is also the clockwise. This is the clockwise moment. Okay, must be equal to P into 1.5. P into 1.5. So MP is equal to, so we have to, my mistake, reaction, we have to calculate reaction. MP is equal to 90 kilonewton meter. MP is equal to 90, so R value will be equal to 60 kilonewton. Here value of R is equal to 60 kilonewton, that is our answer. So my dear students, in the question number 21st and 22nd, in the 21st question, I have applied the compatibility condition, deflection at C is equal to 0. Deflection at C is equal to 0. And in the second question, I have just applied the moment summation of algebraic sum of all the moments is equal to 0. That is okay. That is the final value. Okay. And P is equal to 180 kilonewton. P is equal to, sorry, R is equal to 60 kilonewton for this particular question, 22nd question. Now let's move towards the question number 23. Please note it down very fast. 23 question. Value of W that results in collapse of the beam as shown in the figure adjoining a moment capacity of MP. This is the ordinary hinge, no plastic hinge is required, no plastic moment is required. So the here plastic moment is required, MP moment is required, no plastic moment is required. So this is basically, if this is theta, this will be theta. If this is phi, this will be phi. Okay. Now W is equal to either 3 theta or is equal to this lateral deflection is equal to 7 phi, that is equal to 3 theta. 7 phi, that is equal to 3 theta. So you can calculate the value. You can calculate the value of W using the same fundamental, using principle of virtual work, using principle of virtual work done. Internal work done must be equal to external work done. MP into phi plus MP into, because here also MP moment is required, MP into theta plus phi. Theta plus phi is equal to, and 7 phi is equal to 3 theta. You can balance the units. W into 7 phi. W into 7 phi. So after putting the values of theta, that is equal to, theta is equal to 7 phi by 3. So here theta you can put the value 7 phi divided by 3. So all the complete equation is in the basically phi terminologies, in the terms of the phi. So here we have to calculate the value of W. So W becomes W ultimate or W collapse. W becomes W ultimate or W collapse. That is in the terms of MP, and after calculation I found the value equals to 13 divided by 21 MP. So my dear students, here our answer number D, option number D is correct. That is 13 by 21 MP. Okay. Now let's move towards the next question. A continuous beam loaded as shown in the figure below. Assume a plastic moment capacity MP, minimum load at which beam would be collapsed. Beam would be collapsed. So two mechanisms will be there. First mechanism IJ may be failed. Second mechanism HI may be failed. Second mechanism HI may be failed. So my dear students, our first possibility is the failure of IJ, and second possibility is the failure of HI. So same procedure is applied. When failure of IJ is there, then I got the answer is equal to 6 MP by L. Why? Because my dear students, this will be the probed end, and when this is failed, this acts as a fixed end. This is a probed cantilever, 6 MP by L. Second possibility, failure of HI is there, but this is fixed and this is also fixed, HI. So when both ends are fixed, collapse load is equal to 8 MPa by L. Okay, this is by the virtue of the fixed ends, or by virtue of the continuity of the fixed ends, 8 MPa by L, 6 MPa by L. So my dear students, here the total minimum load, hence the minimum load is equal to 6 MPa by L. If I am repeating this question, this is our probed cantilever. When this is filled, probed, it will behave as a probed cantilever, and when this is failed, when this is failed, then this will behave as a, you can say, fixed beam. So for the fixed beam, value is same, that is 8 MPa by L, and for probed cantilever beam, 6 MPa by L. For probed cantilever, this value is 6 MPa by L. So the final value is equal to 6 MPa by L. Final value is equal to 6 MPa by L. Now question number 25. The plastic collapse load. Basically the same condition is there which I had discussed with you people just before 10 minutes. So at this particular situation also, mechanism 1 and mechanism 2 will be formed. Mechanism 1 and mechanism 2 will be formed. So mechanism 1 is nothing, that is one plastic hinge at fixed support, second plastic hinge below W. So this mechanism is formed. Then our load will be equal to basically in that particular situation, load is equal to 6 MPa by L. 6 MPa by L. Now mechanism 2, I am going to discuss mechanism number 2. Mechanism number 2, one plastic hinge at A and second at D. So one plastic hinge at A and second plastic hinge at D. Now this condition is there. So for this condition, W is there, and this deflection is equal to L by 3 into theta. Let us suppose that this is theta and this is our phi value. So and this is also equal to 2L by 3 into phi. Yes or no? So from here you can calculate MP values there and MP values there. After calculation I found the value equals to 4 MP by L is equal to PU, 6 MP by L is equal to PU. So from here PU is equal to 4 MP by L. So the minimum value is taken 4 MP by L. Hence true collapse load is equal to 4 MP by L is our answer. That is the minimum value. Okay, now let's move towards question number 26. When the triangular section of a beam as shown in the figure becomes a plastic hinge, means here area becomes the same. So this area and this area becomes the same, then this is our plastic neutral axis. So area for the compression zone must be equal to area for the tension zone. This type of problem I had discussed with you people very clearly, and compression zone is half into B into H, means half area of the total area, that is BH by 4. So either compressive force or tensile force is just simple area into stress. Stress is sigma y either for the plastic section or for the elastic section. BH sigma y divided by 4 is our answer. So BH sigma divided by sigma y by 4, BH sigma y by divided by 4. So B option, A option is correct. A cantilever beam of length L, width B, depth D is denoted, and concentrated load is applied at central vertical load. If yielding starts at load P, then collapse load is equal to, as we know that shape factor is equal to MP over My, MP over My, and my dear students, for a rectangular section this is 1.50. MP is equal to collapse load into length divided by applied load or the normal load into length. This value is equal to 1.50. So in general case we can say that collapse load is equal to 1.5 times of the applied load. Collapse load is equal to 1.5 times of the applied load, that is B option is correct. A cantilever beam of length L is concentrated, if the yielding starts at load P, then collapse load is equal to, obviously here the same calculation has been done that we had discussed during the plastic hinge length discussion. Okay, now question number 28. A propped cantilever beam, and basically the same values there, that is 6 MP by L. Now question number 29. This type of problem I had discussed with you people, and during the discussion of the you can say during the discussion of theoretical portion. So vertical load is always twice the horizontal load. Collapse load required for development of a beam mechanism. Only the beam mechanism is asked. You can calculate the beam mechanism using a mechanism for only for this hatched portion, only for this portion. Now let's make the beam mechanism. Here the plastic hinge will be developed, and horizontal load will not do any work. Here the plastic hinge will be developed. So this is our 2P value, this is L, this is L, this is MP, this is MP. Since length are simple, theta, theta, this is our theta, and this is our theta. This is moment is 2 MP, sorry, moment is at the junction, only simple moment is there, at the junction simple moment is there, at the junction simple moment is there. So in general, my dear students, 2 MP into theta plus MP into theta plus MP into theta, MP into theta here, MP into theta here, 2 MP into theta plus theta here must be equal to 2P into L into theta. Why L? Because this deflection is generally L into theta. So after solution I found the value, I found the total value 2 MP, 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 that is 2, 2 is 4, 5, 6, 6 MP into theta, 6 MP into theta, 2P into L theta, theta to theta cancelled out. So P ultimate is equal to 3 MP by L. Only by the beam mechanism we have to calculate, and the value is 3 MP by L. Value is 3 MP by L. However, sway mechanism, this is okay. So in beam mechanism, horizontal load will not do any work. In beam mechanism, horizontal load will not do any work. However, in sway mechanism, the vertical load will not do any work. That is the simple thing. So this was question number 29. Question number 30. Fixed beam subjected to UDL over entire length. UDL over entire length. Obviously, bending moment at supports is always more than the bending moment at center. Bending moment at center. So bending moment at supports bending moment at supports must always be more than bending moment at center. Must always be more than bending moment at center. Therefore, option number C is correct. Hinges are formed initially at A and C and then at B. So, sequence of plastic hinge development. Sequence of plastic hinge development. Initially, the plastic hinge is developed at A and C, then at B. At A and C initially, then at B. Plastic hinge will be developed at B. This type of problem we had discussed during the discussion of theoretical portion for the fixed beam cases subjected to UDL over entire length. That's okay. Now, question number 31. Shape factor for a rectangular section, that is a simple thing, that is 1.50, and the plastic section modulus ZP is given, shape factor is given, plastic moment capacity is given, yield stress of the build material we have to calculate. So now let's discuss the solution. This is our last question of this our unit number 7. Here ZP is given. ZP is 4.8 10 to the power minus 4 meter cube. MP is given 120 and yield stress we have to calculate. Shape factor is given 1.2. So MP, as we know that sigma y into ZP. Sigma y into ZP. So sigma y we have to calculate 120 into 10 to the power 6 whole divided by 4.8 into 10 to the power minus 4. To convert this one, 10 to the power 9 in mm, value is 250 megapascal. Value is 250 megapascal. So my dear students, this completes your syllabus as well as questions of unit number 7. Thank you so much. All the very best for your examinations. Thank you again. Keep learning. Thank you.